And I have the pleasure to invite, unfortunately, some of our invited people could not come today because there is a meeting in São Carlos of the National Association for Advancement of Science, and they had to be there. But I would like to invite to the table Professor Osvaldo Sakayanagi, who is the clinical director of the hospital and one of our collaborators in this project. Also, of course, Professor Geraldo Duarte, who is the head of the gynecology and department. Professor Fernando Cunha could not come today. I would like to invite Professor Baffa, who was the former director of this institute. And Professor Cavalli, too, of the gynecology. We have very important business here that will be talking to you in this meeting, and I would like to recognize the presence of Professor Thomas Helst from MIT, from the scientific page for us, and Professor Jorge Vassos from Cambridge. Our good friend and collaborator, very important for us in everything we do, Professor Celeste Dias from Neuroscience Department and Hospital in the University of Porto, in Portugal. Thanks to Celeste, we started working in this area, and she has been our guru in all this work. Professor Danilo is doing his PhD in Cambridge. He comes from São Carlos. Ron Wakai is a very good friend from Madison, Wisconsin, doing work in RMI and beautiful new techniques in brain physics and in general. Professor Wakai was a good friend of ours, thanks to Professor John Cameron, who was very important for the start of medical physics in Brazil and Latin America, in fact. Together with Professor Baffa, we worked, I think, something like 12 years in Trieste, organizing medical physics for the developing world. Thanks to Professor Abdul Salam, the Nobel Prize in Physics, who was our good friend there for many, many years, until he passed away. Professor Baffa was the director of this medical physics course there, and we are very happy to have him with us, and Ron Wakai. We have many other. I would like to recognize the presence also of Dr. Varsos from Greece, a neurosurgeon, and his wife, psychologist, Esmeralda. I cannot say your name in Greek. It's Magda, okay. Smaragda. That means emerald. So we are very happy to have you with us. I think we have to start now. And I would like to call Professor Tom Helst to start as a special invited talk to us. I think we should sit in the other places. You have a microphone?
I can use a microphone, but I cannot use my regular voice. I don't know whether I need this. You can't hear me like this. Oh, because of the transmission. Okay, otherwise, okay. So I will oblige. Thank you very much for the invitation. It's a great pleasure to be here. It's the first time that I'm in Brazil, and I'm thoroughly enjoying the hospitality and the great weather, actually. When I came, I heard over again that apologies because it's winter over here and that it's very cold. I come from Boston, where our winter looks like this. And this tile on the right-hand side is taller than I am. So MIT prides itself of never closing, but in the last winter we actually closed for 3 days because there was too much snow. And just to give you another indication is this is what I had to do in order to get out of my house. So all of this suffice to say that I really enjoy your winter, right? And if you ever want to come to the East Coast of the United States, you might want to stay away from anywhere between November and March, right? So our summer is much more like your winter. But I'm not here to talk about the weather. I'm here to talk to you about intracranial pressure monitoring. And I understand that it's a somewhat diverse audience, so I want to give you a little bit of a background to put into context the rest of the talk. So from an engineering perspective, here's our brain, and this is the brain parenchyma, what we usually think of as the brain. But the cranial cavity contains essentially 3 components. It's the brain parenchyma itself, so the neural tissue. It's blood, so the arterial blood supply and the venous drainage. And then we have cerebrospinal fluid. And what you can't see over here are these cavities, which are called ventricles or cisterns, and the space over here surrounding the brain, which is filled by the cerebrospinal fluid, which is a transudate from the blood, proteinaceous fluid, that gives buoyancy to the brain. And also supplies, has many functions, also supplies nutrients to the brain. It's generated at the level, or we think it's generated at the level of some of these ventricular spaces, and then it circulates through passageways and around the brain, and then it gets reabsorbed at the level of the venous system. There's a pressure associated with that. So if you were to put a catheter into that space and you were to measure the fluid pressure, you would measure a pressure. And the pressure ordinarily is between 7 and 15 millimeters of mercury. And that pressure is called the intracranial pressure, so the cerebrospinal fluid pressure. As I said, normally it's around 7 to 15 millimeters of mercury, and treatment is indicated intracranial pressure rises above 20 millimeters of mercury. And the reason why that is the case is because there's a relation. Now I'm going back. There's a relation between brain injury and an increase in intracranial pressure. And traditionally, this has been conceptualized through what was known as the Monroe-Kelly doctrine. What has been thought of so far is that the brain and the calvarium, the skull, essentially, is a fixed enclosure. Now, through some work that's being done over here at this university, also in Sao Carlos, we might actually no longer believe that doctrine. We'll have the talk later today where we actually see that there might be some elasticity. But whenever there's an excess volume of CSF, of the tissue or the blood, you actually see that the intracranial pressure is rising. Right? And this could be in a case of traumatic brain injury where you have cerebral edema, you have a hemorrhage where you have excess blood, brain tumor where you have a mass lesion, or hydrocephalus where you have excess CSF. Right? So brain injury can lead to an increase in ICP, which makes ICP a marker of brain injury or damage to neural tissue. But the reverse is also true. If you have an ICP increase, that can actually lead to further brain injury. I will talk a little bit more later about the relationship of intracranial pressure to cerebral perfusion pressure, where the cerebral perfusion pressure is the pressure that actually drives blood flow through the brain. If ICP rises, cerebral perfusion pressure goes down, meaning that in the absence of intact autoregulation, the brain is actually starved of oxygen and nutrients. So that's not good. It can also lead to secondary brain injury through this deprivation of oxygen, and excessively high ICP can actually lead to displacement of brain structures within the skull, particularly into the spinal column, which is a herniation of the brainstem, and then can lead to respiratory arrest, coma, and death. So we want to measure ICP, and we want to control ICP. One way of measuring ICP is through a lumbar puncture. where you actually insert a needle through the deep muscular tissue of the lower back. You try to insert the needle into the part of the spinal column where you have the cauda equina, so you're not damaging the spinal cord itself, and then you're measuring the opening pressure. The assumption here is that the pressure that you would measure at the level of the ventricular space is the same as the pressure at the level of the spinal column. There are some assumptions and there are certain things that you need to rule out in order to actually do this kind of measurement. It's a spot measurement, meaning that you only do this once and you actually get the opening pressure, then you withdraw the needle, the insertion site heals, and that's it, end of story. What if you want to monitor intracranial pressure? So what if you want to measure intracranial pressure over long periods of time in patients, for example, who have a brain injury? Well, you take your favorite drill, you drill a hole into the skull, and then you pass a catheter blindly from that insertion site towards the center of the skull. There are neurocritical care intensivists, neurosurgeons in the room who do this all the time. And when I talk to them, it's like, oh, it's no problem. You just drill a hole, you put it in, boom, you have it, right? But obviously, you would only do this in patients who are very, very sick, which means that a large portion of patients in whom the measurement could actually be beneficial, could actually guide treatment, do not receive this. There are variations around the theme depending on where you actually place the catheter and what type of catheter you actually use, but they all have different accuracies vis-a-vis the gold standard measurement. Some of them are discounted because the measurement accuracy is actually quite poor. So if we had a non-invasive way of estimating or measuring intracranial pressure, what could we actually do? Well, we could do triage at the point of first patient contact, whether that's the battlefield, whether that's the football field, whether that's the emergency room, whether that is the ambulance. We could actually do immediate assessment of intracranial pressure. We think that the brain is important, so we might also want to measure variables that relate to brain. Once you can do this at the point of patient contact, you can do in-time and evidence application of therapy, meaning that if you can actually measure that the pressure is high, you can immediately start intervening, doing therapy, essentially, either giving a drug or putting the patient in therapy. And you don't have to wait for neurosurgical consult. Long-term monitoring without the risk of infection, obviously, if you have a hole in the skull, that's a potential route for infection, and you don't want to do this for a too long a period of time. But the big point is over here, is the expansion of the tissue. Because the current measurement modality excludes a large fraction of patients in whom the measurement could actually be very important, whether that's mild and moderate traumatic brain injury, migraine, pediatric patients, hepatic encephalopathy, and so on. So the way that I usually, for the clinicians in the audience, the way that I usually compare it is the advent of the pulse oximeter. Right? Before we had the pulse oximeter that gives you 97% oxygenation of blood, you had to look at the mucosal membrane. Right? Well, the baby's a little blue, well, the baby's a little red, but you couldn't actually titrate therapy to it ourselves. That's just one of it. Once we actually had the pulse oximeter, it became everywhere. Every hospital, every patient contact, we measure blood oxygen. We can do the same, I think, we can do the same with ICP. All right. So how have we gone about trying to assess intracranial pressure non-invasively? Well, one way it has been done in the past, and here I'm talking about the past part of the title of my talk, is that you have a physiological variable that correlates with intracranial pressure. There are many variables that correlate with intracranial pressure, and you try to establish a mathematical mapping from this variable that you can easily measure to intracranial pressure. Once you've established that mapping in a large enough patient population, you can then prospectively apply. What are some of the technologies that have been used? Ultrasound time of flight through the skull. So you just put ultrasound through the skull, and the propagation velocity is directly related to the pressure of the medium that it goes through. Visually evoked potential. So you're flashing some lights in front of someone, and you actually measure evoked potential. And those potentials have also been shown to relate with ICP. Tympanic membrane displacement, there's an otoacoustic reflex at the tympanic membrane. So if you give a little chirp, the vibration of the tympanic membrane is related to ICP. People have looked at MRI features, features of arterial blood pressure, features of the cerebral blood flow velocity. This has all been investigated, and the key criticism thereof is that it's really not truly non-invasive. And the reason why is because in order to go from here to here, you have to have invasively measured ICT to go through this loop and to identify the mapping that actually relates the physiological variable that you can measure to intracranial pressure. And depending on the patient population on whom you have invasively measured ICT, this mapping might actually be different. It's not quite clear that this mapping is the same for a patient with traumatic brain injury who has an ICT of 40 versus a hydrocephalus patient who has an ICT of 50. Okay. So the criticism is that training-based methods require invasively measured ICT. And another criticism is that you're really strongly dependent on what I call the richness of the underlying training base. Right? You have to have hundreds and hundreds of patients. And the group that has the largest number of patients is a group at Cambridge, where George is currently, it graduated from, Danilo is currently. We have 200, 300 patient cases, right? So it's not, even when we talk about richness of data, you're really actually still in an era of relatively sparse data. There's one technology that has recently been developed, which is actually quite clever, I think, and that's why I want to highlight it, which is calibration-free, meaning that you actually do not have to have a reference. And what happens here, this is was developed by Professor Ragauskas in Lithuania. And what I'm showing you over here is the orbit. Here's the eyeball. Here's the pupil. Here is the optic nerve. And then you have the ophthalmic artery coming through here. And the ophthalmic artery has an internal part, or a part that's internal to the cranial cavity, and a part that's external to the cranial cavity. What Professor Ragauskas recognized is that if I actually use an ultrasound beam and I measure the flow velocity in the extracranial portion and the intracranial portion of the ophthalmic artery, certain features of that flow velocity are different. And they're different because the external pressure external to the ophthalmic artery in the intracranial portion is intracranial pressure. The outside pressure in the extracranial portion is essentially atmospheric pressure. And what he recognized, if I actually apply pressure on the eyeball until I balance the pressure, the outside pressure here with the intracranial pressure, then the features of the flow velocity waveforms in these two portions should be essentially the same way that you measure arterial blood pressure through auscultation, trigonomanometry, right? So you balance the systolic pressure with the external pressure. And then you listen for characteristic sounds. Well, here you don't listen, you just look at the flow velocity profiles in the extracranial portion and the intracranial portion. They validated this technique in neurological patients. This was published 2012. They have recently come out with another publication. And the performance statistics actually look very, very good. A mean estimation error of 0.1 millimeters of mercury, standard deviation of the error of 2 millimeters of mercury, which is excellent compared to some of the invasive methods that are still being used. So I think this method has potential, although some clinicians actually think applying pressure to the eyeball might not be all that great an idea. Nevertheless, the performance statistics all the way up to about 20 millimeters of mercury are quite convincing. You need a trained operator. So you need someone who not only knows how to do transcranial Doppler ultrasonography, but you also need someone who actually can do this in 2 depths. You need a 2-depth transcranial Doppler machine, so that's capital equipment, that's very expensive. And it's not suited for monitoring. So it's not continuous monitoring, it's a spot measurement. But the question is, would you rather have a little bit of pressure on your eyeball, or would you have a big needle in your spinal canal? Right, so this is the trade-off. So we will have to see where this method actually stands up. Another class of methods that have been developed have to do with measuring cerebral blood flow velocity with transcranial Doppler ultrasonography and arterial blood pressure, and then using a mapping to get non-invasive ICT. Bernhard Schmidt in Germany, and in conjunction with the Cambridge group, was one of the first ones to propose this type of approach, and has subsequently used by others, Xiao Hu at UCLA, and Pupo's group in Montevideo. all these methods require training on non-invasively measured data. So all of these methods fall into the category of machine learning. We've asked ourselves, what if we actually don't use a mapping over here? What if we actually use a mathematical representation of the underlying physiology? Right? So rather than actually learning from the data, what if we actually assume a priori or build a model on our assumption of or on a knowledge of physiology, and then we try to estimate parameters of this model? We're getting a little bit more concrete. What I mean by this is mechanistic representation of the relevant physiology that links these two input waveforms to this output waveform. The model should have a small number of interpretable parameters. It should be identifiable in real time, and the parameter estimates should be robust to noise in the data. And what I mean by this model is shown over here. Here's the physiological representation that you can find in an anatomy textbook. So we see the lateral ventricles that I talked about over here, where CSF is generated, the third ventricle over here, the fourth ventricle, and then circulation. If we put ourselves in the shoes of an engineer, right, and we do one layer of abstraction, we say, well, we have the skull, we have the three compartments that I talked about at the beginning. We have the brain tissue, the CSF, and the blood supply. We have the cerebral blood flow going in. We can measure an arterial blood pressure over here. We have the venous pressure over here. The intracranial pressure is over here. One key observation is that veins are very thin-walled. And veins cannot really withstand a negative transmural pressure, meaning if the outside pressure is higher than the inside pressure in the veins start to collapse. But it's not a static collapse in a dynamic system like this. It's actually a dynamic collapse. And that establishes intracranial pressure as the effective downstream pressure. So when we talk about cerebral perfusion pressure, we talk about arterial pressure minus intracranial pressure. We don't talk about arterial pressure minus venous pressure. In most other organs, when we ask ourselves, well, what drives blood through this organ, we say, well, it's the upstream pressure minus the downstream pressure. Right? But here it's different. Here it's the upstream pressure minus the outside pressure. It's called the Starling resistor phenomenon. And we see it in flow limitation, for example, in forced exhalation. We see it in flow limitation in venous return to the heart. So it's a physiological phenomenon that's fairly well recognized. And then if we take another level of abstraction, we're still engineers. Okay? Another level of abstraction, we can say, well, why don't we represent it in terms of a circuit? I won't ask you to write down the differential equation, but I want you to recognize that what we are doing here is really a one-to-one mapping. Right? We have cerebral blood flow, arterial blood pressure that we represent as flow over here and the nodal voltage. The compliance over here is really the elastic properties of the arteries and the surrounding brain tissue. So it's a lumped representation of the entire system over here. This resistance over here is really the resistance to blood flow. And so it's a fluid resistance. The transmural pressure across this capacitance is the arterial pressure minus the intracranial pressure. See over here. And the perfusion pressure through this resistance is arterial pressure minus intracranial pressure because of the Starling resistor phenomenon that I've just mentioned. Okay. So we're going from an anatomic physiological representation like this to an engineering representation like this. The arrows over here represent the fact that there's dynamic autoregulation that's going on, so the capacitance and the resistance can actually change on the basis of what is going on inside of the brain and with the blood pressure. Right? So these are not constant. So once we have this representation, here's the name of the game. The question is, can we measure arterial pressure? Can we measure cerebral blood flow, or as we will show, cerebral blood flow velocity? And then can we estimate RC and ICP from the actual waveforms? Right? And if we estimate them, do they have any resemblance to what we would actually measure in basic? What are the measurements that we have available? Well, in a neurocritical care environment where we treat patients with traumatic brain injury, subarachnoid hemorrhages, and so on, we have invasively measured arterial blood pressure, and we can measure cerebral blood flow velocity. Not cerebral blood flow or volumetric cerebral blood flow, but the velocity of that. And we can measure these as waveforms. This is actual real data. This is arterial blood pressure. This is cerebral blood flow velocity, blood pressure in millimeters of mercury, cerebral blood flow velocity in centimeters. This is our input data. Now, in the previous slide, I've assumed that I actually have the pressure at the level of the brain, meaning the middle cerebral artery, for example, and I have volumetric cerebral blood flow. What I'm telling you here is I have arterial blood pressure, but at the level of the wrist. It's going to be different from what I actually would measure at the circle of Willis, for example. And cerebral blood flow velocity is certainly different from cerebral blood flow. You can go through the math. There are certain adjustments that we have to make in our estimation, the routine, in order to actually match this pressure to the pressure that you would measure at the MCA and the fact that we have flow velocity. But in essence, the estimates are ineffective. So here then is the summary view. We measure arterial blood pressure at the level of the wrist. We measure cerebral blood flow velocity in a major cerebral artery. That could be the middle cerebral artery, posterior anterior cerebral artery. Then we use the model, the circuit model, to estimate RC and ICP on a window-by-window basis. We can actually also do it on a beat-by-beat basis. And we get estimates of non-invasive ICP, R, and C. There's no population parameters or training, so it's not a data-driven approach. It's really identifying these parameters for each individual subject that's in front of you. There's no learning within the patient. It's just like pulse oximetry. You put it on, you get the measure. And there's no calibration required. So there's no free parameters. So when we developed this technology, we reached out to a collaborator, Marek Czosnika, who is well known in these circles, and he made available data to us. We got data from 37 comatose severe TBI patients. Cerebral blood flow velocity was measured with transcranial Doppler, either on one side or on both sides. Radial artery pressure was measured with an intra-arterial catheter, and ICP was measured with a parenchymal probe. Now, if you know Marek, then you know that he is a little suspicious of these kinds of things, and that he said, well, why don't I give you cerebral blood flow velocity and arterial blood pressure, but I will not give you intracranial pressure. You generate intracranial pressure, and then you tell me your intracranial pressure, and then I will make the true intracranial pressure available to you. So we had a truly blinded study of estimating intracranial pressure. I should say that, you know, the model that I showed you was a toy model that we just actually tried to play around with in order to understand cerebrovascular physiology. So at this stage, we didn't really know what to expect. So before I show you the summary view, here's one case, and there are many other cases if you're interested. This is a paper that recently came out, and we hope that the next follow-on paper is going to come out very soon. It has been accepted. What I'm showing you over here is one 23-year-old male. Patient was severely sick. The blue is the measured ICP, and the red is the estimated ICP. And I emphasize that we didn't have access to the blue when we measured when we estimated the red. The range of normal ICP is over here. This is known as a plateau wave. But quite frank, you know, you see that the patient is very sick because the intracranial pressure is very high. But our estimate thereof actually tracks the plateau wave very well. There are certain error criteria associated with that, and we can actually argue or discuss whether these discrepancies are clinically relevant or not. But we went through the estimation procedure, and here's our Bland-Altman plot. So when we looked at the bilateral TCD results that we had a bias of about 1.5 millimeters of mercury. So that's the mean error between our method and the method that was generated in the measurement. Standard deviation of the error of about 6 millimeters of mercury. And we looked at about 1,700 comparisons in 30 patients who had bilateral TCD. This is certainly not good enough to replace the current gold standard. However, it's already on par with some of the invasive methods that are still being used in emergency departments. So whether you have a hole drilled into your skull or you just have a blood flow velocity measurement, here the error statistics are about. In our recent study, we were actually able to reduce this to about 0.5 millimeters of mercury and this to about 4 millimeters. That was subarachnoid hemorrhage cases. So here we're talking about severe traumatic brain injury. Now we're also looking at subarachnoid hemorrhage and hydrocephalus. Another question is not really about tracking intracranial pressure continuously, but to say whether the patient actually has a high intracranial pressure or low intracranial pressure. So that has to do with intracranial hypertension. So intracranial hypertension is usually defined as ICP greater than 20 millimeters of mercury. And if we declare ICH on the basis of non-invasive ICP greater than 20 millimeters of mercury, on all 2,700 data pairs, we get a sensitivity of about 83% and a specificity of 7%. So sensitivity to the engineers, probability of detection, specificity for the, sorry, sensitivity, conditional probability of detection, specificity is 1 minus the conditional probability of diagnosis. So when we actually went with these to our neurosurgery colleagues, they say, well, not really good enough. It's kind of on the right path, but not really good enough. I mean, no one would actually make decisions. Okay, fine. But if we allow ourselves to average temporally, right, if we don't actually make the decision on every individual data window of 60 beats, if we say, okay, so let's record for 5 minutes, and then we average 5 1-minute interval estimates, then our sensitivity goes up to 90% and specificity. So we're getting into the right ballpark. Obviously, you would like a sensitivity to go up 98, 99%. But these were the first evaluations on data that we actually didn't collect ourselves. So now we're actually in the process of collecting a lot of data in the neurocritical care units in and around Boston and control for some data acquisition parameters. So I want to wrap up. And this here is a statistics that provides a lot of motivation to me. Hydrocephalus, as I mentioned at the beginning, is a condition in which you have essentially excess CSF. So you have too much CSF in the brain, and there's no cure for that. There's only one treatment available, which is to place a shunt into the cerebrospinal fluid space, to have a valve over here, and then to drain cerebrospinal fluid into essentially your abdomen or the cardiovascular system where it gets reabsorbed. Okay? This technology here is saving lives. There's no question about it. It's absolutely fundamentally transformed hydrocephalus. So that's the good news. The bad news is over here. This is a long-term study, and I don't have the attribution here. It came out 2 years ago. Anyone who's interested, let me know. I'll find it for you. But what this shows is the fraction of failure-free shunts over about 260 months. What this shows is over the first year, about 40% of all of these shunts fail. Over the first 2 years, about 60% of them. Meaning that over the course of a year or two, you have a high likelihood of having to undergo neurosurgery. There's no electronics, there's no sensing mechanisms on these devices, meaning that the patients have to become symptomatic. Get a headache, nausea, vomiting, and then they might have to go through neurosurgery. This is a great application for non-invasive intracranial pressure monitoring, because you could essentially do a quick measurement, non-invasive measurement of intracranial pressure, and that would mean that the patient is fine, or the patient might actually have to go for it. And I think as engineers, we should be able to do better. Okay? So where do I see this field progressing? I think we're starting to think of ICP, or intracranial pressure, as a cardinal vital sign. The same way that we take blood pressure, heart rate, respiratory rate, temperature, blood oxygenation. We should be measuring intracranial pressure every time we interact with the patient. And we, as engineers, should think about technologies that allow us to do that. I also think that while we all focus on the neurocritical care environment, what I'm trying to tell people is we are focusing on the neurocritical care environment because that's where we have invasive measurement, and that's where we can actually compare to the gold standard. But ultimately, I think the applications of highest impact are outside of the neurocritical care. That we will find, that we will establish a lot of fundamental physiology by being able to measure ICP in other patients. Where is this field heading? What I'm very excited about is the evolution of microelectronics. What you see over here are industries, what I've shown you here, is industries that have been fundamentally disrupted by microelectronics. Whether it's watches, whether it's pocket calculators, whether it's big desktop computers to laptops, telecommunications. I tell students in my class, what you don't realize is that you have more computational power in your pocket than the Apollo space mission had going to the moon, by an order of magnitude, if not more. Right? And I think the next microelectronic revolution will be in healthcare. Whether it's home healthcare, whether it's revolutionizing hospital healthcare. What I'm very excited about is work that's going on over here in Brazil, in the Mascarenas group, on non-invasive intracranial pressure monitoring using very low-cost technology, namely strain gauges, to measure the expansion of the skull. We'll hear about this later on, more and tomorrow also. But I think this is where the future is coming. Very low cost, high throughput technology for intracranial pressure monitoring. With that, let me finish, but I cannot finish without one advertisement. I've laid out the challenges. Next year, we will have a conference in Boston, which is called the Intracranial Pressure and Neuromonitoring Conference. Happens once every 3 years. So I've given you the challenge. I expect all of you to show up at this conference and to show your solutions. With that, I thank you for your attention, and I hope to see you in Boston next year. Thank you. I don't know whether I've gone way over, but I'd be happy to entertain questions.
Yes, there's mind if I have this one. Before, I would like to recognize the presence of an important collaborator of ours, Professor Luisa Silva Lopes, who is here, who is an expert in hydrocephalus. I'd like very much to thank her for coming.
Just a quick question. Last time I saw a stent was a very simple device, like a little rubber balloon that you open under pressure and then the fluid will be drained. I wonder if there are any developments with MEMS for this kind of device. I mean, something that you could activate and work as a pump and not be just a passive device.
Yeah. So I think there are a lot of people who've thought about this. To the best of my knowledge, nothing has transformed or transferred into the clinical environment. The valves are very simplistic. Exactly, it's like a ball with a spring, right? Essentially, that's what it comes down to. In the United States, I don't know how it is in other domains, in other regions. Cost is an issue, and people have tried that technology, but wanted to make a lot of money from it. Right? And so that didn't work. I do agree with you that that technology, and that's why I actually brought it up, is not only the non-invasive ICP, but also the whole hydrocephalus shunt technology is very ripe for re-innovation and for major innovation. And I think whether it's material science, whether it's some smart electronics that you can actually, very low cost, but smart electronics that you can put on the shunt would go a very long way.
Any other questions? Ron, were you asking for a question? Or? Okay. Any other question? No? Okay.
How do you overcome cases in that patients have the temporal window blocked for the acoustic probing?
Yeah, so that is a problem, right? So the question is, in transcranial Doppler ultrasonography, you have a few windows where you can actually shine ultrasound, essentially transmit ultrasound through the skull. The skull is a very high impedance, so you're actually losing a lot of energy, and there's a fraction of patients, especially in the elderly, where you don't get sufficient signal back in order to actually do the ultrasound. What we've actually done is that's a problem. But what we've done is we can actually look at other vessels, right? And one of the exploratory stages of one of our studies, we've actually tried to actually insunnate the internal carotid from the neck up, or even look at the intracranial portion of the ophthalmic area. And the estimates that we get are not too different from the ones that you would actually get from the MRI. So there are alternatives. Thank you.
Okay. I would like to ask you a question too. But you did not mention the MRI people working in non-invasive.
So I briefly went over MRI. So there's a group in Chicago/Florida that have built very elaborate fluid dynamic models of essentially the blood pulsation into the cranium. So if you think of MRI as a volumetric method, right? So with each blood bolus that is injected from the cardiovascular system into the brain, right? You can measure the pulse pressure with an arterial line or with the blood pressure cuff even. And volumetrically, you can actually measure the expansion of the vascular space. So from that, you can get a measure of elastance. With that measure of elastance, then you can go through elaborate fluid dynamic computations to actually get intracranial pressure. The reason why I didn't dwell on it is MRI is expensive. So in order to actually do this, you need an MRI scan that is gated to the cardiac pulsation, and you actually have to go through a lot of computations to do that. It's certainly not anything for monitoring, and even for a spot measurement, it's very expensive. So it's thousands of dollars. So that's why I think that it's unlikely for that technology to catch on.
The other question, Tom, is related to the analogical circuit that you. How about the nonlinearities that you find and the complex analysis of this? That is probably going to be the next step in the whole interpretation of the.
Correct. So the circuit model that I've shown over here, if you forget about these arrows over here, is a linear circuit, right? But we only assume the linearity of the circuit for a window of about, I would say, 30 to 60 beats. So what we do is we actually acquire 30 to 60 beats of waveform. Then we apply our algorithm to estimate RC and ICP. And then we get one value out of ICP. And then there's another 30 to 60 beats worth of data where we also assume this model, but it might be completely different in terms of C and R. We make no assumptions that the C and the R and the ICP that we assume in the second window has any relation to the C, R, and ICP of the previous one. So in fact, if you actually look at this temporally, it might actually be a nonlinear circuit. It's that only in every time window we assume that it's a linear circuit. It's that the relationship between ABP, CDF, and ICP is captured through this model, right? But over time, we do not assume that the linearity actually occurs. But I agree with you that assuming that the whole system is linear is probably a challenge.
Any other question? Well, we thank very much, Professor.
Thank you.
Helen, good to be here. Thank you very much. I'd like to call now Dr. Gustavo Frigieri to present his paper. Dr. Frigieri is a postdoc in our group in São Carlos and here, and has been very important for the development of all the techniques that we try to develop for non-invasive. And I thank him very much for it. Thank you.
Thank you for our invitation. I'll just put my pointer here. Thank you for our invitation. I will talk a little bit about our work with the development of a non-invasive monitor to intracranial pressure. Nowadays, how Professor Thomas told in his presentation, we have just invasive methods to monitor intracranial pressure in hospitals. This is an example of what we need to do to monitor the intracranial pressure. we have mainly three kinds of sensors. That's subdural, intraparenchymal, and intraventricular sensor. In all cases, you need to drill a hole in the skull and put sensor in intracranial space. We have some problems with this kind of methods, like the infection risks. That's a very important point to the invasive method. This method here in Brazil is very expensive. We have a high cost of sensor, equipment, the needs of a good thing to use this kind of methods, and the infrastructure to use the invasive method to monitor intracranial pressure. So, because this is just used in extremely critical cases to monitor the intracranial pressure. Here's a picture of our first experiment with Professor Mascarenhas 9 years ago in his house at São Carlos, where Mascarenhas put a rubber balloon into the intracranial space, and with an air pump and a manometer, he starts to increase the pressure inside the balloon and monitor the skull volume change with this strain sensor. This was the first experiment that shows that we can use the skull changes to monitor the intracranial pressure. This was the result. We can see here the strain values, or we can see that here is the change in the skull volume, and here the pressure measured inside the balloon. The black square is the change when we are increasing the pressure inside the balloon, and the red circles when we are decreasing the internal pressure. We can see that here we have a linear result and without hysteresis. So we can start to use this protocol to monitor the intracranial pressure. We developed in the past 9 years 2 different sensors. The first one is the minimally invasive, where we glue the sensor on the skull. So you just need to cut the skin and glue the sensor on the bone. We don't need to do the trepanation. And here, the non-invasive sensor, where we put the sensor on the skin, and we don't need to do trichotomy. It's so easy to use. We'll show. We have now 3 different models of equipment to monitor the intracranial pressure. We can also measure arterial blood pressure and other parameters. Here I am showing a monitor with 2 inputs, and we have software that shows the intracranial pressure tendency and the intracranial pressure morphology. I don't believe that you can see, but here we have the ISP morphology with P1, P2, and P3 that we will show in next slides. We don't have yet the absolute value of intracranial pressure. We just monitor the tendency of intracranial pressure in the time and the morphology of the signal. The morphology of intracranial pressure is very important because we can use this information to assume if we have a good or a poor cerebral compensatory system. We did a lot of tests with animals and humans to prove that our method was working in comparison with the invasive methods. Here I will see 2 animal experimentations where you use the lumbar infusion of saline to increase the intracranial pressure, and in this case I was testing the minimally invasive sensor and the invasive sensor to compare the results. So in this case you used 7 male Easter rats, and we did 2 consecutive infusions. And here in first figure, we have the result from the invasive sensor, and here with the minimal invasive sensor. We can see that we have a good correlation between these 2 signals, with a Pearson correlation around 0.86. We did the same with the non-invasive system, the comparison with the invasive system, with a lumbar infusion of saline, and in 3 consecutive injections we have this response with a Pearson correlation around 0.88. We don't have the absolute values yet, so we have a lot, many focus. One of our focus is the analysis of the ICP morphology. So I will talk a little bit about this. Intracranial pressure has a very specific morphology with 3 components, P1, P2, and P3. P1 is the first, that's from the systolic cardiac pulse. The second, P2, is the tidal wave that shows how is the blood circulation into the brain. And the P3 is the closure of the cardiac valve. When you have a reduced compliance of brain, we have a change of this morphology. The P2 starts to be bigger than P1. So this is one way to use our method to indicate a increase of intracranial pressure and a reduced compliance. Here we have a figure from our work with Celeste in Port. One patient that is showed here. In green we have the results from the invasive sensor, in red from the non-invasive sensor, and yellow the arterial blood pressure sensor. We can see in this case that this patient has a P2 bigger than P1 or a reduced compliance. We can see that you have a similar morphology with invasive and non-invasive sensors. We start to study this waveform analysis with new mathematical tools, and I would like to invite Dr. Junior to continue with this presentation with his results.
Well, I will be very, very brief. As Gustavo said, the idea here is to analyze the waveform of and compare the waveform of the ICP invasive and the non-invasive to see if we can extract some information that might be clinically relevant to the clinician. Our ultimate goal is to actually estimate the ICP, the invasive measurements from the non-invasive measurements. So this is the idea. But today, I have to warn you, so this is preliminary results. We are just starting this work, and what I will show here today, so my goal is very modest. I just wanted to show you that the ICP and the non-ICP uniforms from this work is very close. And I start to analyze this data from Portugal that Gustavo recorded with Celeste and Rodrigo. And we have in this set 7 patients with traumatic brain injury. They measure the ECG, the ABP, the ICP, and the non-invasive ICP and the pressure of CO2, as you see here in the middle. Well, I have no idea how this works, but okay, here, right, in this 10 seconds window, and then here 60 seconds window. we have in this patient, so the only exclusion criterion that I used was that if any of these waveforms were not present, and then I exclude that data. Otherwise, the data is include that in the analysis, independent of the quality, right? So you might see later on that some points are not very. Can you help me here? So I don't know, it stopped work here. Yes, I can just, you know. It doesn't work. Okay. The method is very simple. Actually, it can be very complicated and has a lot of parameters that you have to adjust. But here I just will briefly explain to you without entering the details. If you have some questions, you can ask me later. And the idea is very simple. I just separate the waveforms in windows and temporal windows, all the waveforms, and then I extract these windows and calculate the power spectrum of this, which is just, you know, here you work in the time domain, and here you translate to a frequency domain. If you are using like this. This is a standard approach in signal processing. If the signals are very, well, they have oscillatory components, so it's very nice to work in the frequency, so you can decompose them and analyzing another way, just to see a little bit better what's going on. And later on, after that, so when you calculate the spectrum, you have still a high dimensional space of 250 dimensions, because you have here 250 points in that. And then what you want to do, the whole idea here, is to reduce the dimensionality of this high dimensional space so that you can see better in trying to keep the global structure of the space in this low dimensional representation. And after that, you can make a model, maybe. So this is this is our goal. We try to first understand the physiology, the data, and try to understand a little bit more of the physiology, and then a little later on try to do the model from that. So this is the ultimate goal. And what you see here is the projection of in 2 dimensions of here, this kind of representation, and from the ICP waveform of one of the patients. And what you can see here, that they have 2 features. These features emerge from the data. In principle, you don't know what they mean. But if you, for example, look at this points here, you see that the power spectrum are different, and you see that the waveform are different. That we are more, that's our main goal. So what we are really very interested in. And from the first patient, here you see in this projection of 2 dimensions, the spectrum or the projection of the spectra from the ABP waveform and the ICP invasive and the non-invasive waveform, right? Each point here represents 10 seconds of the data, so the power spectrum of the 10 seconds of the data. And you can see that you can separate a little bit. Of course, this ABP is not the ABP from the periphery, right? This BP is measured somewhere else, and is a little bit difficult to compare, but you can see that this cloud of points of the non-invasive and the invasive ICP are really close. Or there are some relationship, as you can see here in this zoom. And they have some structures also. But the most here, you know, you might find nothing very interesting, but when you look at the dynamically, sorry. Well, I have a video here, and I will ask you, Gustavo, again to help me to play them, right? I'm sorry, I'm an engineer. I don't have any familiarity with technology. Okay. Okay. Okay, so what you see now is here is for one patient, the projection of the spectra in these 2 dimensions, and you can see here the time, right? It's almost 8 days of these projections, and you see that when the ICP spectra changes, you'll see that the non-ICP also changes. Sometimes it loses tracks and come here because the signal is not very well, but most of the time they are close together. And if you look at the second video, when you have one idea of how the waveforms are changing in a shorter time scale, you can see here the 3 waveforms changing. You can see the power spectrum here changing, right, as the projection is changing there. And you might see that sometimes the waves are very close together. And if they are not close together, so this is our goal, based on the data, try to understand what how they are related. So in green you see the invasive ICP, in red the non-invasive ICP, and in gray is the ABP. It's the opposite, I'm sorry. So okay, this here I'm showing is normalized automatically. Okay. And what you can see here is the same projection in this 2-dimensional space from the other 6 patients that we have in this data set, right? And then you see that the pattern, I don't have the video for all of them, but you see that the pattern of the separation, the superposition of them, of the 2 waveforms are very similar in all the patients. And of course, we might try, it's what Professor Thomas said, it's a data-driven approach, and we have to actually has a very, very large data set to come out with a model that will represent the patients well, reliably, independent of the pathology and the physiology, right? So this is the. I'm sorry. This is all that I have to show you. But as you can see, our goal is to build a model to estimate the waveform of the ICP from the non-invasive ICP. And this would be very interesting because, as Professor Thomas said, the method is very, very low cost, and we can put everywhere. And if we can estimate something that is interesting to the clinician using this equipment and these techniques, then we have a very good tool. Thank you very much.
I forgot to tell you that Dr. Julho Spavieri is an important part of our group, theoretical group. He made his PhD in Germany studying insect vision, where he did a lot of work on bioinformatics. So now he's dedicated to our group in São Carlos and here, and I thank him very much for his collaboration. Any questions? Yeah, Professor Baffa.
have one question for Gustavo and another for Junior. So how do you compare the bandwidth of your system and the one you use invasively? That's for Gustavo. And for Junior, have you tried to use fractal analysis in your data? Because you have like those peaks, and so this looks like you can get away better.
In Porto, we use the non-invasive sensor in patients that needs to use the invasive sensor too. So patients enter in the Porto hospitals with traumatic brain injury, for instance, and needs to do the intracranial pressure monitor, put the invasive sensor, and after this you start to use your non-invasive sensor in these patients. So these patients stay in UCI for many days, where we are monitoring with the invasive and non-invasive sensors and acquire the data with ICM Plus, that's a software from Cambridge, and after we do the kind of analysis.
I would like also to recognize the presence here of other collaborators of ours, especially Master of Science and Engineer Rodrigo Andrade, who's here with us, and also Master student Rodrigo, another Rodrigo, and I thank them very much for being here. And let me see other colleagues here with that have been also Engineer Diogo, who has helped us very much in the organizing the instrumental part, and Francisco Talarico, where's him? He's not here now. Okay, here, please raise to show your face here. Talarico is a very important part of the group with his song. And now the next talk, any other question about this presentation? Okay, the next talk is by Professor Baffa, Instrumentation for Measuring Magnetic Fields from the Brain. It's a great pleasure to have Professor Baffa with us because he has been the pioneer of medical physics in Brazil. You are. Done a lot of important work in many areas of medical physics and biophysics too.
You are raising the kick. Okay, good morning everyone. I'd like to start by thanking Sergio Mascarenhas, our mentor and professor, for all the efforts to having this meeting today here to discuss several physical techniques to study the brain. So my goal is to give a presentation to the next talk that will be given by Ron Wakai about a new kind of magnetometer to study the magnetic signals from the brain. So he'll be talking to you about magnetoencephalography and what are the principles behind it and the present instrumentation. So you'll be able to appreciate what will be the changes that's about to come and to change this area. So the outline of this talk, it's this one. I will give you a little bit of background about how electric and magnetic fields are produced by a set of neurons, and then what kind of information we can get from EEG and MEG, the intensity of the typical magnetic fields produced by the human brain, so you can appreciate how difficult it is to do this kind of measurement. And then I will give you a short history of the instrumentation and a survey of different magnetometers that we have today. And finally, Ron will talk to you about the future of MEG. So when we talk about electric and magnetic signals of the brain, we have to think about neurons and how they work. So neurons for us that are physicists, they are more like the hydrogen atom when we want to understand the quantum mechanics, or the silicon atom when we want to understand solid-state physics. So that's the base unit for the brain, where many physicists had to work and physiologists to understand what are the physical processes behind it. And from that, we can build to more complex systems. So we know that neurons are connected to other neurons by dendrite connections. And if I can, how I do this? Oops. Okay. Okay, here. Okay, so we have the dendrite connections here. We have the body of the cell, and then we have the axons here. So when those connections, they can be excitatory or inhibitory, and as a result of all the chemical interaction we have here, we can have a post-synaptic potential here, and after that we can have an actual potential. So when we look at this, from the physical point of view, we have an electric current that will flow in this direction in the body of the cell, and after that we have another current that will flow down here. So this is a dipole current, and this is a quadrupole current. So if we measure the potentials that are associated, that's what we get. So we have this peak associated with the post-synaptic potential, with this width and this intensity, and a much sharper and higher peak for the action potential. The question is that if I want to measure something far from the cell, this signal here falls much faster than this one. So what we do, what we measure when we do EEG and actually also MEG, is this kind of electrical action that happens in the axon. So that's our goal. We are going to measure magnetic fields that are associated with a small current that appears in the body of the cell. Okay, some equations. So everybody knows from second year physics, if there is a current here, we can use the Biot-Savart law to calculate the magnetic field that will be produced at this point here. And this field will be perpendicular to the plane formed by the current vector and the distance. So it will be point up in this case. So we can plug in the current in this equation, and that's the intensity of the field. We have to find what is this internal current that flows within the neuron, and we can do some simple calculations and calculate the gradient of the potential there. That's the electrical field. Multiplied by the conductivity, we get the current density, and if we multiply by an area, we get the current. So we have all the elements here to go from the magnetic field to the current that's produced within the neuron. We can do a little bit more of calculation, insert this gradient of voltage in the equation, do the integrals, and finally we get this equation here that shows us that the magnetic field will be proportional to this p-value here. That's actually the current times the distance it exists. So that's what we call the electric dipole, or the current dipole. Okay. So in general, we can express the magnetic field because it's a vector by means of this equation here, where we have the electric dipole multiplied by the distance vectorally, divided by this distance here. And that's the expression for the magnetic field, and this is the expression for the potential. So they are very much similar, but there is a little difference that this product here, so here it's a vector product, and this is a vector, and this is a scalar product, and this is a scalar function. So what do we do when we have this kind of information? So we can project and get the three components of the magnetic field. Usually we measure the Z component, and Z in this case means that if I have a plane, and in this plane I have a current and a distance, I'll be measuring the field that's perpendicular to this plane. So that's the Z direction. And once we can measure something, we can map this property. So here I show you if I have a current dipole, suppose I have like a saline tank, and I place there a small current dipole, I can use a voltmeter and map the potential in this surface, and I can use also a magnetometer and measure the magnetic field. And if I do a map, I link all the points with the same potentials here, and I link all the points with the same vector intensity here, I can produce a map like this. And what's interesting in this map is that there is a relationship between the map and the orientation of the dipole. As you can see here, there are two maxima in this potential map, here and here, and the current dipole points along this direction. And if I map the magnetic field, then I have a maximum here, a minimum here, and then we have the current dipole pointing perpendicular to this line that connects the two extremes. So we can use this kind of map to somehow know where the current dipole is. And we'll see soon why this is important. So if I have a current that's flowing in this direction, in this case entering the field of the plane of the screen here, we know by the right-hand rule that the magnetic field you be circulating here, will be circular lines. If I measure the z component of the field, I will have one maximum here and one minimum here. And if I look this in terms of maps, that's what I'm going to see. See, you have one maximum here, one minimum here, and the current dipole is pointing in this direction. So what happens now, if I have different positions of the, or different depth of the current dipole, we can see that as I go deeper and deeper, the intensity of the extreme will diminish and it will be more spread around. So by making the map and measuring the separation between these two extremes, I can know the depth of the current dipole. And this is, as we see, will be very important. So when we study signals from the brain, I told you that we are measuring signals from the neurons. And the question is, what kind of neurons and how many of them can I measure it? So first, there are two extremes of cells that I can show here in the brain. Some of them are of this kind. You know, they are like stars pointing in all directions. This kind of cell won't produce any magnetic field because of the orientation of the currents. We have currents flowing in all the directions, so this current here cancels this one will cancel this, and this one will cancel this in terms of magnetic field production. So we don't have any contribution from those cells. But there are some cells, like the pyramidal cells, that are very well aligned. So this one has a linear orientation. We have a current flowing in a preferential direction, and this one will be producing magnetic fields. So when we measure magnetic fields from the brain, that's the typical cell that we are going to measure. The other question is how those cells are organized within the brain. So we know that the cortex has about 2,000 square centimeters, and we have to fit the cortex inside the brain. So there is no space for it. What nature did, it folded this thing and placed there. So the brain is full of those convolutions here, and about 2/3 of the cortex are in this kind of morphology here. So these are the kind of orientation that you'll be giving a magnetic field outside the brain. And this kind of orientation here will give a potential more intense than the other. So when we do magnetic measurements from the brain, that's the kind of cell we are going to measure. That's the kind of orientation we are going to measure. Okay, so in order to measure a signal, we have to have a reasonable current. Otherwise, we don't have a strong magnetic field to detect. And this number of neurons that should fire at the same time and produce an electric current should be on the order of thousands of neurons. So our spatial resolution, it's about a few millimeters, and the numbers of neurons involved in the process will be in the order of thousands, 10,000 or so. In summary, we have an electric activity in the neurons, and this electric activity can express itself by two means. One is the electric potential, and that's what we measure when we do a EEG, an electroencephalogram. And in this case, we are measuring the current that flows outside the neuron within the surrounding tissues and reach the skull so that we can measure with electrodes. And when we do an MEG measurement, what we measure is the internal current that's flowing within the cell. So that's the difference between the two methods. And this can cause us a huge difference in terms of location of the source. So if I do an EEG measurement, I'll be measuring potentials here at the skull, and the current that reaches this point has to travel different tissues within the brain with different electric conductivities, and when it does that, it gets deviates. So I can measure one signal here, and I don't know exactly from where it's coming. When I do MEG, the brain is essentially transparent to the magnetic fields, so the field I measure outside here has no influence of the different layers of conductivity here, so I have a better chance to locate where the source is. And why we stress this point about the location of the source, because most of these techniques, they are meant to be used to study the brain non-invasively. So I have here some place. So the idea is that I can expose the brain to some stimuli. Some area will be activated. So I have a simulation task here. So neurons will fire, and then as a function of this, I will have changes in the metabolism and in the vascular approach here of nutrients and so, and I can make a functional map of the brain. So when you do a functional MRI, we measure the different levels of oxygen here. When you do a near dot image, we're going to measure changes also in hemoglobin here. We hear about the stone. And when we do MEG and EEG, what do? We measure the electrical activity of the neuron. So that's more, let's say, that's more precise in terms of locating where the activity is, because sometimes the changes in the vasculature won't follow very close where the neurons are. They have to diffuse or perfuse there. Okay, so that's why it's important, this kind of technique. We can actually study non-invasively what happens with the brain. Okay, that's transparency that shows you the kind of problem we have to deal with. So here we have in the vertical axis, we have the intensity of the magnetic fields that are produced biologically. And here we have the frequency range. So this big peak here is the spectrum of the magnetic fields produced by the heart that we call magnetocardiogram. And here you can see the MEG, so the magnetoencephalogram. That's this intensity here. For you to appreciate the difficulties we have here, that's the Earth's field. The Earth's field, magnetic field, is on the order of 50 microtesla in the northern hemisphere, and in our region it's about 20 microtesla. And so this signal here, it's about 1 billion times weaker than the Earth's field. On top of that, we also have a lot of magnetic noise. So we live in a civilization that's commanded by electricity. So electricity is everywhere. And so that's a typical environmental noise in a laboratory. Even the Earth, as it turns around itself and around the sun, will produce some magnetic noise. So as you see, we have a signal that's weaker than all this noise and the static field we have around. So we have to develop techniques to measure it. So we need to have a very sensitive sensor capable of measuring this signal, and we have also to deal with noise problems. So the challenge is more or less like going outside now and try to see the stars. The stars are there, but we don't see them because the sun's present and blocks our view. So if we go at night, then someone hides the sun for us and we can see the stars. So that's our trick. We have to find some way to hide the noise and try to see the stars. Okay, a little bit of history now about the magnetometers. So the first magnetic measurement from brain signal was done in 1965 at the University of Illinois by a very well-known physicist named David Coyne. That's at MIT now. So what David Coyne did, he built this aluminum shielded room, and he built this pair of coils here. So if you ask any physicist to measure a magnetic field, what method he will try first, so probably he or she will wind a coil and try to see if this coil is capable to measuring the magnetic field that's varying here through the voltage that appears in this coil. So a few years later, two other physicists had done the same experiment and had measured the signal from the heart. So David Coyne decided to try the same thing for the brain. So as you see, this is a very big magnetometer. The dimensions here is on the order, the diameter is on the order of 10 centimeters. We have here about 2 million of turns. I don't know if you try to do a coil, but you have a very thin wire and winding 2 million of turns. It's quite likely that you break at some time and you have to start over again, right? So it's not an easy thing, but it's doable. And it also, he put some container here that you could cool the coil so that you could lower the Johnson noise and do the measurements. Okay, how he managed to see alpha rhythm. So he did the following experiment. He put the magnetic detector here close to the occipital area where you have the most strong alpha activity. And then he took some EEG leads, took this to a system for do averaging, and the magnetic signal was triggered by the electric signal. So the electric signal was much intense and easier to detect. So he used this as a trigger for the magnetic signal, and that's the raw data with just one shot. And this is what he got of 10 minutes of signal average. Nowadays, when you want to do this kind of thing, it's trivial because you have all this nice electronics and any computer, anything, any AD board, you do this almost instantly. But at those times, signal average machines were a very serious piece of equipment. You have to play a lot with to make it work. So it was quite a challenge at that time. So a few years later, in 1971, David Coyne moved to the MIT, and then he got in touch with another very well-known physicist in the area, James Edward Zimmerman, that had invented this squid. And then he was able to measure alpha rhythm. This is a real-time tracing, no averaging, you can see the spindles here of the alpha rhythm. And this was possible because he had made a much better shielded room. In this case, the shielded room was not only made of aluminum, but also with some magnetic material that could screen the Earth's field and all the other fields around. And also he used this SQUID. So SQUID is an acronym for Superconducting Quantum Interference Device. So it's a device that was invented in the early 70s by James Zimmerman, and it worked based on the principles of superconducting. And this is just one drawing that was made by Jim Zimmerman. Jim Zimmerman visited our lab several times because his brother was at our department, Bob Zimmerman. So he helped us a lot of times when he was alive. So this is just a drawing showing the model of the squid. So it's actually just one ring of superconducting material with a weak link here with a very thin resistive barrier. So what happens is that when you apply magnetic fields to this ring, it somehow talks to this circuit here, and you can detect the signal. So it's very sensitive. It has a sensitivity on the order of 10 to the minus 34 joules. You can measure flux here that are on the order of 2 times to the 10 to the minus 15 Weber. So it's an incredible sensitive device. And by using this, then Coin was able to measure this kind of signal. So this was a breakthrough in the area, and after that, many labs start to working in biomagnetism and detecting signals from the brain, from the heart, from the liver, whatever you can see a magnetic field or a current, you can try to measure a magnetic field. And so that's to show you one very simple system. This is the one we have here. So squids, in order to work, because they are superconducting, they have to be placed inside a vessel that contains liquid helium. So liquid helium has a temperature of 4.2 Kelvin, and you place all your instrumentation here in this bath, and then you cool the system, and then you can measure magnetic fields. So to give you an idea of the scale here, so that's one person, and in this case we are measuring signals from the stomach. So when the stomach contracts, it produces a current, and we can measure the magnetic field from this current also. So this is a single channel. We use this same channel, this same system, to study the brain. So that's how it started, and this is how Ron and I got involved in biomagnetism. So I was doing my postdoc there in Madison, Wisconsin. Ron was recently hired there, and we were studying magnetic fields that were produced by pain stimuli. We didn't have we have just one channel, and we had to make a map. So the challenge then was to measure magnetic fields in different parts of the skull, and then we could make that magnetic field map and try to locate where this activity that was evoked by pain will be produced. And this was a very challenging experiment, because in order to make this map, we had to map about 30 different points. We had to apply maybe about 50 or so stimuli to the finger of the person. It was a painful stimuli. So after being a volunteer in this session, you'll be shocked about 2,000 times, and you'll be really mad. But then we managed to get some signals. So this is the magnetic field detected. This is the electric field detected. And then when it was mapped, we could overlay the position of the equivalent current dipole in the MRI image. So this work was from '88, I guess, right? And that's the status at that time of what we could call today a multimodal image. So it was very much like a work of art, because you have to get the image from the MRI, do a lot of work, and then almost by hand try to locate where you are and position there. So those things nowadays, they are much more easy to do and quick to do. Okay, so of course, if you want to study the brain, just having one channel is terrible, as I told you, and the area rapidly moved to what we call now multi-channel systems. And this is the system that Ron has in his lab. He has 237 channels, so the person can lay here. One hemisphere can be placed in this sensor, the other hemisphere can be placed in the other sensor, and you can detect signals from both sides. Or you can use just one unit to map the chest or whatever you want to do, or some bomb swamp, and this is inside the shielded room. There are more, there are systems with more channels, and that's the state of art now. You have like a helmet, and then the person, you stick the head here, and you have all those coils that are placed around the head, and you can collect signals from 150 points simultaneously or even more. So these are two systems. This is one in Japan. We did some experiments there one time. And this is the system that's now being, I think that's the only one that's being sold commercially today. Those systems, they have to be housed inside a very large shielded room. The room is quite expensive. You can maybe use between $500,000 and $1 million, depending on how much shielding do you want it. And that's the typical signal you get. So you evoke some magnetic fields, you do some averaging, and after you average your signal, you can do the map. And when you do the map, you can see you have what we call this butterfly pattern here. That's the stimuli we applied in both ears, and that's the kind of auditory evoked field. And you can then represent in different ways. You can do just plot the average signal, and you can see we have some actives here in this area, some activities here. You can see that in this side, the signal is pointing up. Here, the signal is pointing down, and here it's almost flat, so our dipole should be oriented around here. Same thing here. And you can do this color contour plot where you just plot the intensity at one time, and that's where one dipole is, and this is where the other dipole is. And you can make a multimodal image and showing the representation of the dipole, overlaying it in a high resolution MRI image. So that's the state of the art, and that's what MEG can give you. You know, we can locate sources within the cortex with very high spatial and temporal resolution. So that's the goal. There is one more complication that I want to show you, and I just went through very quickly. Those systems, in order to work, we need liquid helium. And for many countries, not the U.S., but except for the U.S., helium is really expensive, and you have to recycle it. You have to recover. And this is just to you to have an idea of how we deal with this recovery problem. We transfer the helium to the dewars, and then the helium will evaporate. We have to collect the helium in plastic balloons like this one, and then compress the gas into the cylinders, and then send these cylinders to a facility that can liquefy the helium, purify, and then liquefy the helium again. So that's a very critical step in this kind of operation. So here in our campus, I have a single channel system. And why I have a single channel system? Because this is the only one I can afford with the kind of budget I have. Because in order to operate this system for 3 weeks, I need something like 65 liters of helium, and I have to do this operation, send those cylinders to 100 kilometers away to be liquefied in São Carlos and then bring back. So that's very discouraging when you want to do this today. And to give you an idea, the cost of helium in Brazil is about $30 per liter. It's not cheap. So it's we have to worry about it. So all of this, I think, is about to change, as Ron will tell you. And I would like to finish by thanking many collaborators. Ron, of course, is the first one. I had done a lot of work in biomagnetism applied to gastroenterology. So my collaborators are from the medical school here, Ricardo, Troncon, and many other people now that are faculty in our department. So with that, I would like to thank you. And if you have any questions, I'll be glad to answer.
Thank Professor Baffa for the excellent talk introducing the theme. So that Ron Wakai will show us a new paradigm, breaking the problem of how to use magnetic fields in the brain. but Professor Baffa did a lot of work here organizing this with great difficulties because of the Brazilian situation of bureaucracy and lack of support and it's really heroic type of work he did here organizing this laboratory here. Any questions?
Well, it's been a long time since I've looked at Maxwell's equations, but do you have to worry about displacement currents? No?
No, because it's very low frequency, so we don't have to worry about that. We have to worry about discontinuities in the conductivity along the brain because sometimes you have currents when flows around and then they can be, but there are models for that.
Any other question? Okay. Thank you very much, Professor. I call now Ron Wakai to talk about this continuation of this problem. Thank you very much, Ron.
Thank you, Sergio. As many of you know,
One second. I forgot to correct. There's a small mistake in the program. Professor Wakai is from the University of Wisconsin at Madison, not Madison University. Okay.
So as many of you know, I've collaborated with BAFA for many years. It's always a great pleasure for me to come back to Brazil and to Ribeirão Preto. So I'm going to talk about using light to measure magnetic fields of the brain. BAFA was gracious enough to give the background to my talk by presenting an introduction to MEG. So my talk will focus on a new type of magnetometer that really has the potential to revolutionize MEG. So the field of MEG has been totally reliant on squid magnetometers. MEG really didn't exist until squids were invented in the 1960s. And it's been a symbiotic relationship. MEG is the most important application of squid magnetometers. But there's no doubt that the high cost of squid technology has limited the growth of the field. There are lots of other technologies that have been tried. There have been some significant improvements in high temperature squids, for example, and magneto-resistive sensors, but really they just don't have the sensitivity that squid magnetometers do. But that changed in 2003 with the development of the CIRP magnetometer, so that's what I'll be talking about. So it's really the first device that has the same or even better sensitivity as a squid magnetometer, and it's a practical technology, a room temperature device. It should be a lot cheaper than squids as well. So atomic magnetometers have been around for a long time, longer than squids, but they just weren't that sensitive or convenient to use. But this breakthrough was achieved in 2003 by Mike Romales' group at Princeton University. And there are now a handful of research labs working to develop this detector, and several small companies. Commercial systems aren't yet available, but there's been a lot of progress made. There are prototypes, multi-channel prototypes that have really good performance that have been demonstrated. So I'll first describe how atomic magnetometers work, and then I'll try to explain how this CIRP magnetometer is different than a conventional one. So there are two operating modes for atomic magnetometers. The mode that you might be more familiar with is the resonant mode, where the spins precess around the magnetic field. So the precession frequency is proportional to the magnetic field, which is very convenient. But the device that I'll describe operates in a different regime, the low field mode, where the precession rate is really slow compared to the relaxation rate. So for that reason, the magnetic field produces just a slight rotation of the spin polarization. Now, conceptually, the magnetometer is pretty easy to understand. So at the heart of it is this vapor cell that contains a vapor of atoms, alkali atoms, and optical pumping. There's one laser that pumps the atoms, polarizes them, and then the spins will rotate in the magnetic field, so they'll acquire a small X component, and then you need some way to detect that rotation. So for example, you can use a probe laser and measure the rotation of its linear polarization, and that will be proportional to the magnetic signal. I won't go too much into that because there are lots of different readout schemes that have been used. So this is kind of a schematic of the first device that was made. And there was, this result got a lot of attention because of the incredibly high sensitivity that they achieved, sub-femtotesla sensitivity. So how does that compare with squids? Well, squids are usually in this regime between about 1 to 10 femtotesla. So even the first device was better than that. So the intrinsic sensitivity is really high, and subsequently they got even better results. But one thing to notice is that the frequency response, the bandwidth, is low. It's lower than what's required for MEG. So it's not a completely fair comparison to a squid, because the bandwidth was sacrificed to get this really high sensitivity. So some details here. This is there's this glass cell that contains the atoms, and you have to heat the cell to produce the vapor, and the heater controls the vapor density, which is a very important parameter. But it's an inexpensive technology because the optical components are standard. They're cheap. The only thing that's costly is the lasers, but those are coming down in price all the time. So some aspects of the physics of these magnetometers can be quite complicated, but it turns out that there's a simple block-like equation that predicts the behavior of the device very well. This is the equation for the spin dynamics, and it's got these three terms. So this one describes the precession about the magnetic field. There's a term for the relaxation. I'll talk about relaxation processes later. And then a term for the optical pumping. So all atomic magnetometers rely on optical pumping to produce the spin polarization. So the electrons with spin -1/2 can absorb a photon and effectively get pumped into the +1/2 state. So the situation is a little more complicated than this because the alkali atoms have nuclear spin. Most magnetometers use rubidium, which has nuclear travels to the nuclear spin, transfers, it stores some of the angular momentum, which enhances the performance of the device. So the atoms are interacting with each other and scattering among these different states, but you get this steady state so-called spin temperature distribution. Now, the atoms in the F=1 state are precessing in an opposite direction to those in the F=2 state. The electrons are oppositely directed. So that partially, but not completely, cancels out the precession. So you get an overall precession because there's a lot more atoms in the F=2 state. So that equation that I just showed you can be used to predict the signal response. So you can deduce that the X polarization, the magnetic field produces this slight rotation, and the X polarization is proportional to the magnetic field over a really, really wide range of fields. You get a response that looks like this, but it's really linear and very sensitive in this region that's much greater than the size of the signals of interest. So this is the expression for the theoretical sensitivity that can be achieved by the device. So what we want is to have the largest number of atoms precessing in phase for it as long as possible. So the sensitivity is proportional to the number of atoms in the cell, but there are some constraints. So for MEG, we want spatial resolution on the order of a centimeter or two, so that's really as large as the cell can be. There's also a bandwidth requirement. You want to measure frequencies up to about 100 hertz or so for MEG, so that imposes a limit on the minimum bandwidth. And I mentioned before that there's this trade-off between sensitivity and bandwidth. That's one difference between a squid and the atomic magnetometer. Squids have really, really high bandwidth. They can measure signals up to RF, microwave frequency. But the atomic magnetometer, if you want to increase the bandwidth, you have to trade off sensitivity. Two other key parameters are the number density, given that the volume is fixed. There's the number density controls the total number of atoms in the cell, and then there's a relaxation time. So normally, you want a high density and a high long T2, and normally there's a trade-off between these two parameters. As you increase the density, you decrease T2, but the SIRP regime gives you a way to circumvent this limitation. So to describe that, the relaxation time is the critical parameter, and it's limited by things like collisions between the atoms, and there's a buffer gas, and there's walls of the cell. But the dominant relaxation mechanism is spin exchange collisions between alkali atoms themselves. That's the spin. And when that happens, you get a precession that looks like this. So if you could isolate the atoms, then they would precess nice and smoothly forever, but in practice you can't prevent these spin exchange collisions from happening, and that reverses the direction of the precession, so you get a total precession that looks like this. So with that, we can understand the surf regime. So that's depicted in this figure here. So normally these magnetometers have been operated in a regime like so, where the spin exchange collisions, the more of them you have, the more it degrades the sensitivity of the device. But in the surf regime, it turns out that as you increase the spin exchange interactions, you effectively turn off that relaxation mechanism. So you can see as you increase the interactions, you start getting something that looks more sinusoidal, and at really, really high spin exchange rates, you get this nice, smooth precession. Notice that it's slower than the intrinsic precession rate, but it's nice and smooth. And this is what allows the device to be really super sensitive. Now, this effect was predicted many, many years ago. This paper was published in 1977, but it wasn't until 2003 that this was actually implemented by the Princeton group. So this is what the initial device actually looks like. It looks like a physics lab experiment, not at all like a device. So it's on an optical bench. You can see it's got these standard optical components. The cell and the oven are inside of this cylindrical shield. There's a holes in the shield for the laser beams to go through. So a lot of the effort has been towards trying to make the devices much smaller and more practical. So one step in that direction was the first MEG measurement, which was conducted by that same group at Princeton. So this was performed in a cylindrical shield just large enough to fit the subject in. This is the cell. They used a single, really large 7.5 cubic centimeter vapor cell. And they measured the output using this photodiode detector array, so that gave them some spatial resolution. The lasers entered through openings in the shield, and they were able to measure a brain signal, an auditory evoked response. That's what most of the groups use, the type of brain signal that they measure, because it's the easiest. You just present some auditory tone through a speaker or earphones. But the signal quality was quite modest. They needed 600, they had to average together 600 trials in order to get the signal. That's a lot more than you would normally record. And this single large vapor cell just isn't suitable for doing whole head MEG studies. It would be good for cardiac measurements or other applications, but really not for MEG. Another effort is shown here by a group at Sandia. So their device is still quite large. But one thing that they were able to show, which is an advantage of the atomic magnetometer, is that you can measure more than one component of the magnetic field with a single sensor. So they measured both the vertical and horizontal field. You can actually get all three components, but the component along the direction of the pump beam has somewhat reduced sensitivity. Okay, so I'll now describe some of the work that I've been involved in. So my background is not in atomic physics, but I've been collaborating with a group at my institution. Thad Walker is the physicist there. And we made the first fiber optic coupled modular device where we have basically single channels that can be arranged any way you like. So this shows the device schematically, the cells here. There's the pump beam, the probe beam, and the polarization is analyzed right here, so that the magnetic field signal is simply proportional to the voltage difference between these two photodiodes. So you can see that the devices, actually we attached it to the bottom of the squid magnetometer in my lab. So the devices are right here. The spacing is about 7 centimeters between the channels, and the performance was really quite good. So these are heart signals, which are much larger than brain signals. They're easy to record. But heart signals from the fetus are a lot more difficult to record. We're interested in this because this is actually the main area of my research, is recording the fetal MCG. And these fetal MCG signals are just as difficult to record as brain signals. You really need to have a device with the same sensitivity, especially to record the small components of the cardiac signal, the P waves. These are really difficult to resolve even with a squid magnetometer, so you can really see how good the performance of this device can be. So more recently, I've been working with a new company that was started by Vishal Shah, who's an atomic physicist who studied at both NIST and Princeton. And he has a device that is very practical and simpler, and yet maintains excellent performance. It just requires one laser, applies a modulation field and lock-in detection to detect the signal. So it's that simplicity requires you to sacrifice a little bit of the sensitivity, but it's still very good. The intrinsic sensitivity is just slightly worse than squids. It's about 7 or 8 femtotesla here. Squids are usually down around 3 to 5 femtotesla. But the signals that are detected are larger than with a squid, because squids sit in a dewar, and you can only get them to within a couple of centimeters of the scalp, but the atomic magnetometers, you can position them closer, and that compensates. So we got really great signals with this device. It was just a single channel, actually a 2-channel device. So there's one sensor right against the subject's chest, and one that sits a little higher that's used for noise cancellation. But this figure compares recordings from the atomic magnetometer and a squid channel. We studied 10 subjects. You can see that how similar they are. They're virtually indistinguishable, both in morphology as well as signal quality. And we recorded brain signals as well. Again, these are auditory evoked responses. And again, this is a direct comparison between a squid and an atomic magnetometer. So, you know, my squid has lots of channels, but you can find one of these large signals. It is shown here, and it's again virtually identical in morphology and quality to the signal recorded with the atomic magnetometer. Okay, so this is kind of just an aside, but you can really miniaturize these devices, and that's been done by NIST. They developed this technology to develop atomic clocks, and it can be applied equally well to magnetometers. So that can open up some completely new applications. You don't need devices this small for MEG. But QSpin will is making devices that should look like this, and you can pack them very closely. This is good enough for MEG or pretty much any biomagnetism application. It should be in the next month or so that they'll test the device in my lab. Okay, so just to kind of summarize some of the advantages and disadvantages of this magnetometer is that it's should be a lot cheaper than squid technology. It operates at room temperature, so you don't need liquid helium, and you can also, the sensors are very accessible. They're not within a cryogenic dewar, so they can be reconfigured. The sensors are small, so you can have a smaller wearable MEG helmet. You can use smaller magnetic shields. And as I showed you, you can record more than one component of the magnetic signal. So there are some disadvantages, but they're not really major. The bandwidth is modest, around 100 hertz, but that's adequate for MEG. One thing I didn't mention too much is that you have to really precisely cancel the ambient fields. So squids can operate in high fields without any degradation of their sensitivity, but if you with these atomic magnetometers, you really have to completely cancel the field down to about a nanotesla or so, or you'll degrade the sensitivity. And it's yet to be seen how reliable and easy to use these will be. So in terms of new capability, the fact that you can access and reconfigure the sensors should be a big advantage. So for example, pediatric epilepsy is a really important clinical application of MEG, but you can see that babies' heads are just way too small for sensors designed for adult heads. So you can really make adjustable helmets with atomic magnetometers. This should benefit other applications like magnetocardiography. You can, again, take the sensors and reposition them to do whatever type of study you're interested in. And of course, the low cost is really critical. It really should allow many new groups to enter the field. So the cost of buying the system, the capital cost should be much lower. Operational costs should be pretty negligible. And I didn't talk too much about the shielding, but Bafa showed you more about the shielding. The cost of the shielded rooms is really high too. There's no point making a super cheap sensor if you need to buy a really expensive magnetic shield. But due to the small size of the devices, you can use these new metal cylinders, which cost a lot less. Okay, so to conclude, it's really just a matter of time before these devices are used for applications that are currently performed using squids. The situation is really, I think, somewhat better than I've shown, because there's a group, for example, that developed a 30-channel MEG system about a year ago. They showed the results. They got really great results, but I can't show it to you because they haven't published that yet. But that prototype looks really promising, as well as the devices from QSpin that I've been working with. So it's I think the first applications that will benefit are things like MCG, other simpler, more cost-effective applications. MEG systems will take a little longer to develop, but really there are no fundamental obstacles. So this is a really promising development in the field. So, thank you.
Ron, for this beautiful talk that opens up new fields. One question I would like to ask you. You talk about lower costs. Can you give us numbers, at least approximate numbers? This Q model, how much does that cost? This.
I think that the systems. I think I wrote an approximate number in there that I think they could cost like 5 times less. You know, I really think like MEG systems cost several millions of dollars, and the new systems, I'm sure they'll cost hundreds of thousands of dollars, but really they should be well under $1 million. I mean, I think something like 5 times cheaper.
Any questions? Any further questions?
I presume with the multi-channel magnetometer systems, you can actually do the pumping and the readout with the same laser. You do not have to scale up the number of lasers that you need, or at least not linearly with the channels.
Right. The pump laser can serve quite a few, usually somewhere between 5 and 10.
Sorry, we are lacking.
The pump laser can pump between 5 and 10 cells typically. But there are, I showed you that NIST device where they have these tiny lasers, and that I think eventually I think they're going to go in that direction, and those lasers could really be a lot cheaper.
Any other questions? Then I have a question. Instead of shielding, how about measuring stray fields in material science and things like metal tubes that go down the sea for oil search? Is there anything applied in material science and defects in solids?
Measuring magnetic
Straight
signals.
fields,
Yeah, that's one thing that I think this device will be used for. It is used for like their geological applications, and they send magnetometers up into space. Like QSPN has a contract with NASA, for example, to do just that.
Not with oil companies.
Oil companies have used squids to do surveying, to do magnetic surveys. They could use this device as well, although this device does not perform as well in large ambient fields in the Earth's magnetic field. So some of the sensitivity would be reduced. It would still be better than existing devices, but it wouldn't show this ultra-high sensitivity.
Very interesting. It's open to many things that could be thought about using this new technique. By the way, I would like to thank the organizer, João Henrique of the Institute, that has helped us with this, and the director, Fernando Cunha, also, and all the team that works here. Been very kind to support us. And thank you very much, Ron, for the beautiful talk. Now, the last talk in this part of the meeting is by Danilo Cardim, who is a Brazilian working in the UK in the brain chair lab of the University of Cambridge. By the way, let me tell you a little story about this. You know, Cambridge University is 800 years old. You know, Newton, Darwin, DNA structure, and a lot of other important things. Now, about 3 years ago, I think, that 3 years ago, they started the new chair of brain physics. And this was given to Professor Marek Zosnica, who has been here in this auditorium giving a beautiful talk on his work. And the presence of George Varsus and our good friends, Dr. Celeste Diaz, they come from the UK too, where they have worked. And Danilo Cardim is also one of our students from Brazil that's doing his PhD. And I want to acknowledge also the presence of Charles Wang, one of our important collaborators in the group of ICP. Charles has been working with us in many applications of ICP. Okay, please.
Thanks, Professor. Firstly, I made some changes in the title of my talk, but I'll still be talking about non-invasive intracranial pressure assessment. And I would
you
like
have
to
to speak a little long. Yeah.
Is that okay? And today I would like to share with you some results from my research in Cambridge, in which I'm a first-year PhD student under supervision of Professor Marek Zosnica, and also under co-supervision of Professor Mascarenhas. So today I would like to show you some results of non-invasive intracranial pressure assessment using a technique which was mentioned here before, which is the transcranial Doppler ultrasonography in traumatic brain injury patients. So firstly, a brief introduction about intracranial pressure. We know that intracranial pressure is the pressure inside the cranial cavity and spinal space at which the central nervous system is subjected. And it has basically 4 components. The first component is the inflow and volume of arterial blood, which comes to the brain. The second component would be the venous blood outflow. The third, the cerebrospinal circulation. And the fourth, the brain parenchyma itself. So about traumatic brain injury, we know that a basic definition of traumatic brain injury would be an alteration in brain function or other evidence of brain pathology caused by an external force. Major causes are related to mainly car accidents, domestic accidents, and also assaults of any sorts. And we also know from the literature that neurological damage from traumatic brain injury, it does not occur at the moment of the impact, but it evolves over the ensuing hours and days, according to the Brain Trauma Foundation guidelines. And we also know that improved outcomes related to traumatic brain injury are obtained when these secondary insults, which resulted from reduced cerebral perfusion pressure to the brain, are prevented or respond to treatment, which nowadays is currently mainly based on the treatment and control of cerebral perfusion pressure. Related to ICP monitoring, we know that CPP, the pressure gradient driving the blood flow to the brain, is an association of arterial blood pressure and intracranial pressure. So, arterial blood pressure is a commonly monitored parameter in any neurological or unit, but ICP is not. So, as it was showed previously, all methods currently applied in clinical practice to monitor ICP are all invasive of different sorts, intraventricular, intraparenchymal, subdural, subarachnoidal. And one of the most common methods are the intraparenchymal, represented by the Codman ICP Express. However, we have this ICP monitor. they are all invasive, and it carries risks of infections and brain tissue damage to the patient in many situations. That's why we don't have this parameter mostly applied in neurological units. So in order to provide alternatives to patients who might benefit from ICP monitoring, several non-invasive ICP techniques have been described in the literature. And one of them that I would like to present today is the transcranial Doppler ultrasonography to estimate the non-invasive intracranial pressure. And we know that transcranial Doppler ultrasonography is a technique mainly dedicated to see detection, to detect changes in blood flow velocity that are caused by vasogenic changes, that is, changes related to blood volume to the brain. So related to the principle of working of transcranial Doppler, here we have this picture showing how we insonate the brain arteries. Actually here it represented by the basal arteries. So here we have the transcranial Doppler probe, which is placed in this region of the skull called temporal window, which are represented by slim layers of bone, which permits the ultrasound wave to reach the brain arteries with few attenuation. And then blood flow velocity is recorded by emitting this high frequency sound wave from this ultrasound probe, and then the wave bounces off to the same probe which is emitting the signal. The specific frequency is 2 megahertz, and this is the mainly used frequency to estimate cerebral blood flow velocity. And there is a relation of flow velocity to the probe, which causes a phase shift in this frequency, wherein this frequency is increased or decreased according to the velocity of the blood. So this frequency can be recorded and be assessed electronically after recording. So on this screenshot we have a typical representation of monitoring of cerebral blood flow velocity. Here we have what we call M mode, which shows the depth of insonation of, and every depth represents a specific artery. In the case of the middle cerebral artery, which is the main artery used for transcranial Doppler assessment, it can be found between 55 and 65 millimeters. And here on the lower panel, we can see the pulse waveform of blood flow velocity in the MCA. So in the blood flow velocity, we can observe a peak systolic and then diastolic, as we can see also in arterial blood pressure waveform. And from this signal, we can extract different related indices, such as the pulsatility index, resistance index, which shows quantitatively and qualitatively the morphology of the flow velocity waveform. So now I would like to present to you the TCD-based and ICP methods that I've been working on during my research. The first method, it's called the black box model method, which was developed by this researcher Bernard Schmidt, which is also a collaborator from our group in Cambridge. So this model the non-invasive ICP assessment using this model is obtained by this mathematical black box model, which is a method that does not use physiological structure, but it's based on a set of mathematical expressions that takes into consideration the arterial blood pressure waveform using linear signal transformation, which is dynamically modified by the relationship between arterial blood pressure and the flow velocity obtained by with transcranial Doppler. So these parameters, arterial blood pressure and flow velocity, act as coefficients to find and continuously update a transformation of arterial blood pressure, which would be the input of the model, and ICP, which would be the output of the model. And this method also provides a full waveform of non-invasive intracranial pressure instantaneously. In the literature, this author also reported the confidence interval for predictions of non-invasive ICP based on this model, which in comparison to direct ICP, the invasive ICP, would be around 12.8 millimeters of mercury in traumatic brain injury patients. The second method I would like to present is a method based on the flow velocity diastolic, so considering only the end diastolic period of the waveform of transcranial Doppler. This method was developed by my supervisor, Professor Children, in 1998, and primarily was dedicated to calculate not the non-invasive ICP, but instead the non-invasive cerebral perfusion pressure. So, in this model, we have that non-invasive cerebral perfusion pressure would be the relationship of arterial blood pressure multiplied by the factor of flow velocity diastolic divided by flow velocity mean, represented by the mean flow velocity diastolic, with a correction factor for traumatic brain injury patients of 14 millimeters of mercury. As we know that ICP actually is the relationship of the difference actually of ABP and cerebral perfusion pressure. If we do have the non-invasive cerebral perfusion pressure, we actually can estimate the non-invasive ICP based on this model. The second method is a concept called critical closing pressure. And critical closing pressure will be more extensively explained by Dr. Varsos in the afternoon. This concept actually denotes the lower limits of arterial blood pressure, below which the brain small vessels would collapse, and then the blood flow to the brain would cease. This method is also based primarily on the estimation of non-invasive cerebral perfusion pressure and takes into consideration arterial blood pressure and flow velocity signal as the main required parameters for assessment. And CVR here, it's the cerebrovascular resistance, which is also an index derived from the flow velocity signal, and CA, represented by the compliance of the cerebroarterial bed, also derived from transcranial Doppler flow velocity signals. So, again, if we have non-invasive cerebral perfusion pressure and also having arterial blood pressure, we can estimate non-invasive ICP. And the fourth method is the method based on the pulsatility index. And pulsatility index, as I said previously, is an index that describes quantitatively and qualitatively the changes in the morphology of the TCD waveform resulting from cerebrovascular resistance changes. So, for non-invasive assessment of intracranial pressure using pulsatility index, we use a cohort of 292 patients, traumatic brain injury patients from our laboratory collected at Adrenbrooke's Hospital, Cambridge. So for this estimation, we had that non-invasive ICP was given by 4.47 multiplied by PI plus a correction factor of 12.68 millimeters of mercury. Given that PI is the relationship between the difference between flow velocity systolic minus the flow velocity diastolic divided by the flow velocity mean. And for PI, there are also other works in the literature that describes the confidence interval for prediction of ICP using not this formula, but previously described formula in different centers. And in case of Bellner and collaborators, a work from 2004, they found a confidence interval for prediction of ICP of 4.2 millimeters of mercury, highlighting that this result was not replicated by any other researchers. So the objective of this study was that because there is a variability in the reported degree of agreement between non-invasive ICP obtained from transcranial Doppler and ICP, we systematically compare the previous four methods that I described with a measured ICP in a prospective cohort of patients we have in Addenbrooke's hospital. So Manchurian methods. Regarding population, we had actually 4 sedated and ventilated traumatic brain injury patients, which were admitted to the NCCU, the neurocritical care unit at Addenbrooke's Hospital between 2013 and 2015. They were consisted of 32 males and 8 females, with population age mean of 35 plus minus 15 years. And the median pre-intubation Glasgow Coma scale of these patients was around 6, ranging from 3 to 14. And the signals collected were arterial blood pressure, invasive intracranial pressure, flow velocity, cerebral blood flow velocity, in a total of 66 recordings. And these recordings, some of these 40 patients had more than one TCD recording during their stay in the hospital. So that's why we have a greater number of recordings in relation to the number of patients. And also, I would like to highlight that this study was approved by the ethics committee in the hospital. So related to data collection and calculations, ABP was obtained at the radial artery and was calibrated at the level of the heart. And ICP was obtained via an intraparenchymal probe. And cerebral blood flow velocity was obtained from the middle cerebral artery bilaterally when possible using this 2 megahertz probe. And for recordings, duration of them was 10 minutes up to 1 hour, and it started from the day of initiation of ICP, invasive ICP monitoring. And all calculations in this work, including the mean values of arterial blood pressure, ICP, and flow velocity, were performed using a moving average window of 10 seconds, and using the ICM Plus software, which is an in-house built software for clinical data analysis. So regarding to statistical analysis, we used Pearson correlations to see the correlation between non-invasive ICP for all 4 methods and ICP, in this case considering only mean values of ICP in millimeters of mercury. We also calculated the 95% confidence interval for prediction of ICP using the Blen-Altman method, which takes into consideration the standard deviation and multiplies it by 2 times. And also the area under the curve of rock curves using the threshold of 17 millimeters of mercury. And the area under the curve under rock curves in this case, they denote the prediction ability of these methods to detect pressures above 17 millimeters of mercury, which is considered an increased intracranial pressure. So for recordings, and also for recordings which mean ICP presented changes greater than 7 millimeters of mercury, in this case we only had 8 cases, we calculated the average correlation between ICP and non-invasive ICP for all 4 methods, considering only trends in time domain action. In this case, we only consider the changes in ICP, not considering the mean values. And we also calculated the correlation between delta ICP and delta N ICP, in which delta would be the difference between the highest value and the lowest value during this ICP change. Now, results and discussion. Firstly, related to correlations between non-invasive ICP methods and intracranial pressure method. For the black box model, we obtained a Pearson correlation of 0.39, significant, with ICP. For the flow velocity diastolic method, we also obtained the same correlation, also significant. For the critical closing pressure method, a similar correlation, a little bit smaller, of 0.35, also significant. And for the PI method, despite previous work which correlated increased intracranial pressure with PI, we couldn't obtain the same results, and in this case the correlation was only 0.15, non-significant. In relation to the confidence intervals for prediction of ICP, which denotes the agreement between ICP and non-invasive ICP, for the black box model we obtained a confidence interval of 9.94 millimeters of mercury. For the flow velocity diastolic method, it showed the greater confidence interval out of the four methods of 14.6 millimeters of mercury. Critical closing pressure was presented a confidence interval of 9.19, and the PI method a confidence interval of 9.62. Now in relation to the rock curves, the area of rock curves are better, they are considered better if the area is above 0.8, which denotes a very high prediction ability to detect pressures above the threshold, which in this case was 70 millimeters of mercury. For the black box model, we obtained an area under the curve of 0.66. The flow velocity diastolic method presented the best performance to detect these thresholds above 70 millimeters of mercury, with area under the curve of 0.7. Critical closing pressure showed the area under the curve of 0.6, and PI was the worst one, presenting area under the curve of 0.43. And we also, in order to find a more reliable method, we took out of these four non-invasive ICP methods, the three ones which presented the best statistical performances, which were the black box model, the flow velocity diastolic model, and the critical closing pressure, and we arithmetically averaged them in order to obtain a new estimator, which was called average non-invasive ICP. So for this method, we obtain better statistical indicators. Firstly, in relation to Pearson correlations between this method and ICP, it presented a correlation of 0.47, significant. In relation to the confidence interval, it was around 0.9, 9 millimeters of mercury. And in relation to the areas under the curve, it showed the best performance out of the four methods, presenting an area of 0.73. And in this case now, I would like to show the correlations regarding only trends in ICP, not actually considering the variations in the mean value of ICP in millimeters of mercury, just considering time trends of changes in ICP. So, as I said before, we only considered patients which presented changes greater than 7 millimeters of mercury. So here in the upper panel, we can see the invasive intracranial pressure. And in the lower panel, this is the first example of the black box model, which in relation to ICP presented a correlation of 0.6. The second method, considering the same period of changes in ICP, presented the flow velocity diastolic method presented a correlation of 0.7. The critical closing pressure, also considering the same period of changes, presented a correlation of 0.85. And the PI method, in this case, also presented a correlation of 0.85. So overall, considering only time domain changes in ICP, the PI method and the black box model presented best correlations. PI was the best in this case. And in relation to the correlations of delta ICP and delta N ICP in considering the mean values of ICP during these changes, they didn't present any significant correlations at all. So coming out to conclusions and remarks, we could see from this study that the non-invasive ICP black box model proved to be the best estimator for ICP in this cohort of traumatic brain injury patients, although all of them showed moderate correlations with direct ICP. The methods based on flow velocity diastolic and critical closing pressure, they showed intermediate accuracy in comparison to black box, and the pulsatility index method presented good correlation only in time domain during variations of ICP. And also this new method based on the averaging of the black box model, the flow velocity diastolic model, and the critical closing pressure, overall demonstrated a stronger statistical indication for ICP prediction. So this study had also limitations. The first that I would consider is the quality of transcranial Doppler recording, which for using the signal to estimate non-invasive intracranial pressure, it's very important not have a signal like this, for example, with noise and spikes in the signal. We need to be we need to have for intracranial pressure non-invasive assessment a very stable and good quality signal. This is an example of a signal that we wouldn't use to estimate non-invasive intracranial pressure using transcranial Doppler. And also, one of the factors that could also interfere in the measurement of non-invasive intracranial pressure is the arterial blood pressure zeroed at the level of the heart. We are considering cerebral blood flow circulation, not peripheral circulation. In this case, a best scenario would be to have the arterial blood pressure at the level of the brain, zeroed at the level of the brain, and also that changes in cerebrovascular resistance, such as that one produces by variations in the pressure of CO2, which is a potent vasodilator, they could interfere also in the measurement of non-invasive ICP. And third, the low range of ICP values, as I showed, we only had 8 cases which presented changes greater than 7 millimeters of mercury, could also consist of a limitation of this study to assess how these methods behave during changes of intracranial pressure. So that's it I would like to present to you today, and thank you very much for the attention.
Congratulations, Danilo. We are
Thanks,
very
Professor.
proud that the Brazilian connection to Cambridge has given such interesting results in a short time. We are very proud that Danilo has a master degree from the Federal University of São Carlos, and now he's part of the group in Cambridge with this result. By the way, I would like to acknowledge the presence of Professor Felix Rigoli of the Pan American Organization, who is the main supporter of our activities here, including this workshop. We are very grateful to Felix, who is an MD and working in very interesting projects in the health system, not only in Brazil, but in Latin America, with all his experience all over the world. Thank you very much, Felix. But going back to Danilo, Danilo did a lot of work here with many colleagues, including he did beautiful work with the new methods of minimally invasive ICP. He did not mention that, but he and Charles Wang and Gustavo were instrumental to develop a new minimally invasive method, which is proving to be very practical. And we hope that our good friend Celeste Diaz will have that in her laboratory in the near future. Any questions from the audience? I have one question. In your rock curve, how can you get the morphology with the TCD method easily? Can you make an analysis of the morphology?
Yeah, I think so. We can use spectral analysis.
And do you have any observation to do about the morphology, like in case where P2 is higher than
we didn't
P1?
apply such an analysis.
Can you talk a little longer?
We didn't apply such an analysis in this work. Yeah.
You have an observation, Tom, with all your tremendous experience.
I just have a comment, and one comment is that the leveling of the blood pressure is an issue, and I was wondering whether that actually introduces some of the biases that you see in your Bland-Altman analysis.
Yes.
But it might have been too fast for me to understand the methodology, but I have a sign error. But maybe we can talk about this afterwards.
Sure.
But an easy way to compensate for that is just to measure the hydrostatic difference between the measurement of the level of the right atrium, where the blood pressure is being measured, and the tragus. So if you look at the hydrostatic column, you can actually subtract that column. The only thing to recognize there is that the gravity of blood does depend on the hematocrit. The hematocrit you should be able to get from the clinical recordings, so that you can actually do an approximate compensation for the blood pressure at the level of the brain rather than the level of the heart.
Yeah, from the beginning of this year onwards in Cambridge at the NCCU, they're applying zero enough arterial blood pressure at the level of the head. Yeah.
Thank you, Daniel. Well, I think it's really a very important clinical issue, the local of measurement of zero or calibration of the arterial blood pressure. And when you just go around all the ICUs, most of them use at that level, and it's very difficult to change this practice. And one of the important things is that when we are changing the head elevation, we want the transducers to go with this change. And so if you keep it at the head level, the beds that we have now are not easy to do and to cope with that objective at every moment. That's why for practical meaning you use the transducer at the heart level. So I think that one of the most important issues in our scientific research is to get to a consensus and to define for this type of research if it is better just to publish with at the heart level and everyone, all of them, all of us, to the same way or not. We take into account the either static pressure, and we always have our patients, unless they have hypertension, but we all have our patients at 30 degrees, the head elevation, and we have the way of measuring the angle at the bedside. But when you just look at the research, sometimes we don't know where they are measuring, and that's the guidelines and things like that have to take into account this.
I fully agree. And if you look actually at the pediatric TBI guidelines, they actually recognize that fact. The adult TBI guidelines are lacking behind. But you're exactly right that when we review a paper, we should actually make clear to the authors that they should state very explicitly where ABP was measured. In the USA, it would be very difficult to move the transducer from heart level to the tragus simply because everybody is calibrated to the level of the heart, right? But if you actually talk about cerebral perfusion pressure and you just blindly use the measurement at the level of the heart, you're overestimating by anywhere between 10 to 20 millimeters of mercury. So that the easiest way is to actually what you said, is to actually measure the vertical distance and to simply subtract. Could be easily done in any patient bedside monitor. Talk to Philips about it, we have talked to GE about it. They say it's a great idea, but it's not in their critical path.
Talking about optimal CPP and targeting optimal CPP.
By the way, there was one time when Tom wanted to do some experiments with a giraffe at MIT. And that would be an interesting problem regarding this question of what the was not approved. They had no space for the giraffe. So, okay. Well, anyway, thank you very much, Daniel.
My pleasure.
Congratulations for your work. Now we have an interval, and we'll be here at 1 o'clock, at 13 p.m. or 1 p.m. and we'll hear Professor Jorge Barços talking about the critical closing pressure of cerebral hemodynamics, and then Professor Celeste Diaz talking about near-infrared spectroscopy in patients with acute brain injury and elevated intracranial pressure. And also we'll hear our colleagues here from the medical school talking about preeclampsia and some aspects of that research we are trying to do here too. And Dr. Ballesteros is not here yet. Dr. Mateus Ballesteros works in hydrocephalus, and so that will be the next session. I hope you'll be with us. Thank you very much for your presence. Cambridge, Greece, the United States too, and it's a great pleasure to have him here. He's going to talk about a new index for cerebral hemodynamics with the critical closing pressure, which was the theme of his PhD thesis recently in Cambridge. Thank you very much. Before you start, I would like very much to thank our collaborators here, especially Maria Vicentini, who helped to organize all this, and she has been very important. Also, Carol Rizzati from our group. Dr. Carol Rizzati is a molecular biologist, and Ligia Frigieri is also one of our great helpers here. Okay, thank you for starting.
Hola para todos. Buon tarde. I hope I said it correctly. Hello, everyone. I would like to cordially thank you, Professor Mascarenhas, for inviting me here to attend this amazing conference. And I would like to thank everybody here for the presence and also the organizers. I said to many of you that it's not my first time in Brazil. It's my second. And definitely it's not the last one. So I really like Brazil. So today I'm going to talk about the critical closing pressure of cerebral hemodynamics. This is the theme of my PhD that I completed recently in the University of Cambridge at the Department of Clinical Neurosciences the same department that Danilo Kardim. And let's see what we have. So first of all, I don't have any disclosure. So let's begin with the outline. So we'll start talking about what is critical closing pressure, or CRCP, and then we'll go on calculating methods of how we can estimate this parameter. So first things first, the concept of CRCP, it's actually a threshold, right? It denotes a limit of arterial blood pressure that's able to sustain the integrity of the cerebral microvasculature. If you go below that value of blood pressure, it will result to a collapse of cerebral microvasculature, leading to a cease of cerebral blood flow, okay, and ischemia. Now, as a property, CRCP, or critical closing pressure, has been denoted to be the sum of two parameters, intracranial pressure and the parameter called wall tension, arterial wall tension. So this presents vasomotor tone, and this is the tangential wall tension. Let me show you detail what I mean. So here you see the cerebral vasculature. So you see here on the big arteries having the TCD probe measuring blood flow. And you see here a window that I put about what critical closing pressure is referring to in terms of the size of the vessels. So we're talking about small arteries up to the level of meta-arterioles that all of them have smooth muscle tone. Okay? So let's say an example. Imagine that we are having a small brain vessel. So you have arterial blood pressure inside with this kind of direction. You have ICP with direction from outside to inside, trying to squeeze the vessel. And you have also the peripheral wall tension, tangential wall tension. So under normal circumstances, arterial blood pressure inside here is higher than the sum of ICP, intracranial pressure, and wall tension. Okay, remember the property that I said before. So if it is higher, it will keep the vessel inflated and open. So everything is good. However, if intraluminal blood pressure becomes lower than the sum of the ICP wall tension, then you're going to have a collapse of the vessel. So the lowest value of blood pressure that can sustain that is the critical closing pressure, CRCP. So let's see about the concept of CRCP and how you can have some classical assessments in order to estimate this parameter. So here we have blood pressure and flow velocity pulse waveforms, right? And the most classical method that was being used in order to calculate CRCP is that you would take the systolic and diastolic values of both blood pressure and flow velocity, the latter obtained through transcranial Doppler. You put a regression line, you have an intercept point of here having the blood pressure. So if you see zero flow velocity, so no blood flow, this point would represent actually the point that's where the vessels close, which is the critical closing pressure. So for this example, it will be around 78 millimeters of mercury. The golden standard methodology, it's derived by analyzing this pulse waveform of ABP and flow velocity in terms of frequency. So you have a Fourier analysis, and you have this kind of formula here, which includes a fraction of first harmonic amplitudes of blood pressure and flow velocity waveforms. This is called the Michel method. So this is the golden standard model methodology. So now I'm going to introduce you to a new methodology, the one that I introduced in my PhD, and I'm going to take you through the journey of various applications on which I applied it. So the concept of impedance CRCP, this is the new methodology that we introduced in Cambridge during my PhD years. It's based on the concept of cerebrovascular impedance, which represents the opposition of the cerebrovascular tree to blood flow. So think about viscous and elasticity properties of blood and arterial wall. So this formula here, I'm not going to go deep into mathematics, includes mean values of arterial blood pressure here and intracranial pressure, which is included here in the cerebral perfusion pressure, which, as many of the speakers before mentioned, is the difference between ABP, blood pressure, and ICP. It includes physiological parameters of cerebrovascular arterial compliance and resistance and heart rate. And in that model, we had two versions, one invasive and one non-invasive. The non-invasive one being considering ICP, it's stable and zero. Based on this new methodology, I created two margins. The closing margin, which is the difference of blood pressure, mean blood pressure, to CRCP, the threshold, indicating how far is the system from absolute ischemia. Similar to that is a diastolic closure matching, with the difference of diastolic blood pressure to CRCP indicates how far is the system from the point of the vessels closing during diastole. So you can see it here on this graph. So you have blood pressure, systolic values, mean and diastolic, and this is the threshold of CRCP. So if that difference becomes 0, so you have the vessels closing during diastole, and if that difference CRCP to mean blood pressure becomes 0, then you have a complete collapse of the vessels. So these are some of the basics, the basic tools that I'm going to use to present the applications. So let's go through experimental applications, and this is the first studies that I did in Cambridge in terms of retrospectively analyzing data from New Zealand rabbits. And this is my first study. Actually, it's about a multi-maneuver experiment for validation of the new methodology. So you have the new novel impedance CRCP methodology being compared to the first harmonic method, which is the golden standard method, under a wide range of variable conditions. That would include cerebrovascular tone and affecting also intracranial pressure. These conditions included 3 basic physiologic parameters. One is intracranial hypertension, second is arterial hypotension, and then a hypercapnic challenge with rising PCA2. Let's see how CRCP behaved. So, in terms of validation, you would see that there was a very high correlation of the new methodology, impedance CRCP, with the golden standard method, so over 0.9. And you can also see, if you see here on the blood outcome plots, that there was a very small bias between the two, especially when you go above 40 millimeters of mercury. So if you think in terms of applications, like in the hospital, right, 40 millimeters of mercury for a human being to have is very low, right? It's almost not impossible. So everything above it, you will see that the difference between those two is very, very, very identical, the two methods. So in terms of experimental maneuvers, as I mentioned, we have arterial blood pressure going down. So this is with introduction of trimethophan, a gag blocking drug, on which you had wall tension being significantly decreased. Why? Because due to the decrease of arterial blood pressure, cerebral perfusion pressure, which is the responsible mechanism for driving blood flow in the brain, was reduced, right? And because that happened, autoregulation kicked in, and you wanted to have this blood flow sustained. So vessels were dilated in order to sustain the blood flow. And this was shown in wall tension being significantly decreased. And this led to critical closing pressure also being decreased in that maneuver. Then in ICP increase, you had a significant increase in critical closing pressure. And here I remind you the property that CRCP is the sum of ICP plus wall tension. And here is an example. You have ICP rising due to infusion of saline in experimental rabbit, leading CRCP, critical closing pressure, to significantly increase. But we also could see that wall tension was decreased. And you can see it also in the table. Why is that? Again, because perfusion pressure, cerebral perfusion pressure, was being decreased with the arterial hypertension, but regulation kicked in, and you wanted to have dilation of the vessels. And that was indicated by the wall tension parameter being decreased. And then in the PSCO2 increase, this is a hypercapnic challenge. So from normocapnia to hypercapnia, we know that PSCO2 is a very potent vasodilator, right? It dilates the vessels. So again, you see that wall tension decreased, dragging CRCP to a decrease as well. Now, the major drawback of all the methodologies, of the previous methodologies, including the ones that I presented, the golden standard method, for example, is that they present negative values. Okay, so CRCP is shown to becoming negative, which is not physiological, because we're talking about blood pressure, right? This has been a severe limitation of the critical closing pressure and how it was applied in the clinical reality. So here I present you 2 examples of how the new impedance method eliminated that drawback. So you see 2 examples of PSCO2 increase. So here you have 2 rapid examples of this increase. Here and here you can see the black line, the thick black line being the impedance method, the new one, being positive, whereas the golden standard method became negative here and here. And this, you could also see that when you have a gradual PSCO2 increase, right? So here, PSCO2 rise, the golden standard method becomes negative, but the impedance methodology becomes, it's positive, physiological, right? So it's both correlated very highly to the existing methodology, but also eliminates a drawback. So now I'm going to present you a very short explanation of how you can have disappearing values of diastolic blood flow velocity in some situations. So many of you, I assume, are clinicians, but for those who are not, so if you're measuring blood flow and you see diastolic blood flow becoming 0 in the Doppler, this situation has been associated with a cerebral arrest, circulatory arrest, and ischemia, and might be death. Okay? So what I want to do is trying to understand whether the CRCP concept can explain that. Okay? So the hypothesis is that we know that when blood pressure goes below the CRCP, blood flow ceases. What happens if diastolic blood pressure goes below the CRCP threshold? Would diastolic flow velocity cease as well and explain that phenomenon that I said? Let's see. Here is an example. So you have low velocity and you have blood pressure as well. This is experimental. So trimethophan here led blood pressure to decrease significantly. And the interesting thing here is that before the arterial hypotension, you had very normal values of systolic and diastolic flow velocity. Everything is normal. But once you have a severe reduction in blood pressure, you can see that diastolic flow velocity, here the red one, has been disappeared. So you see visually what I mean. And here's an example of the DCM depletion. DCM, I remind you, is the difference between diastolic blood pressure and critical closing pressure. So you see, again, diastolic blood pressure going down, and when it was below the threshold of CRCP, the one that you want to avoid and be over it. At the same time, of course, the difference becomes negative, but very interestingly, diastolic flow velocity becomes 0 as well at the same point. And this led us to think a little bit further, and this is the result. So we think that the exhaustion of the diastolic closing margin is linked with the reduction of diastolic flow velocity. So you can see in these two figures here, when the DCM goes down, diastolic flow velocity goes down. So this is all the rabbits as a cohort, and here as average. So both of them are linked. Okay? And when diastolic flow velocity becomes 0, this is at the same point when DCM becomes 0 as well. So how does this mean, how this can be interpreted in terms of clinical reality? It means that once you see diastolic flow velocity becoming 0 in Doppler, it means that the vessels, the small vessels, distal to the big isolated vessels, are collapsing or have collapsed during diastole. Okay? And it means that the diastolic blood pressure has come below the threshold of CRCP. So you know when you see that you have a collapse of the peripheral vasculature, microvasculature. And this can lead, if the situation continues, it can lead to a severe ischemia and death as well. Now, the second point that I want to present to you is about what's the effect of the exhausted diastolic closing margin on the cerebral blood flow. So what you can see here, we focus on the left figure, you can see that when perfusion pressure, which again, I remind you, it's a mechanism that drives blood flow, is decreasing, we are already below the lower limit of autoregulation, so there is no mechanism in terms of autoregulation sustaining blood flow. Flow velocity decreases. But after you have the DCM becoming 0, so after diastolic blood pressure has touched and went below the closing pressure, this relationship, it becomes more passive. The slope becomes steeper. And this could be exactly the same seen in laser Doppler fluorometry, so both with big arteries and also with topical measurement of blood flow. What does it mean? It means that with decreasing perfusion pressure, an exhausted diastolic closing margin is being associated with an accelerating decrease in blood flow. So once the vessels are closed during diastole, that means that the overall blood flow is becoming even more fastly decreased. And this led me actually to propose a change in the Larsen curve. I don't know how many of you know the Larsen curve, but this is a very well standard and established concept in blood flow with perfusion pressure. So what I say, it says that in this area here, where we have the lower limit of regulation and upper limit of regulation, autoregulation here works, perfusion pressure changes in order to sustain blood flow in a specific level. Okay, so everything is good. But if you go below the lower limit of autoregulation, or above, respectively, any change in perfusion pressure becomes passively transmitted to blood flow. Okay? So the black line is what the Larsen curve has been for so many years. So my hypothesis and what I introduce here is that there's another breakpoint around here where the DCM, the diastolic closing margin, becomes 0. Okay? So the relationship of blood flow to perfusion pressure becomes even steeper. Okay? So you have a higher risk for ischemia. Now let's go quickly to clinical applications. So let's talk about CRCP during plateau waves. So the aim of the study here was to characterize the pathophysiological phenomenon of plateau waves, which are quick rises in intracranial pressure, right? Using the concept of CRCP and trying to quantify the ischemic risk during the hemodynamic changes caused by these plateau events. So let's see what I could say about the plateau events. So this is when ICP becomes very quickly and very highly increased during the plateau. And let's see what the other parameters are doing. So critical closing pressure, which is the sum again of ICP plus wall tension, becomes significantly increased during the plateau wave. Wall tension, which represents vasomotor tone, becomes decreased. Why? Because you have vasodilation trying to compensate for the decrease in cerebral perfusion pressure. So you see that decreasing. The interesting thing is that arterial blood pressure during this event was static. There was no significant difference. So you can see here that the difference, the distance of blood pressure to CRCP, denoted as the closing margin, becomes decreased on top of the plateau wave. Okay? So if blood pressure touches CRCP, blood flow is 0. Okay? And using statistics, you could see that from baseline to plateau, the closing margin did decrease significantly, promoting an increasing risk of brain vessels collapsing during these plateau waves. Then I forgot to mention that this application was in traumatic brain injury, and we still stay in traumatic brain injury, trying to see the relationship and what is the relationship of both CRCP and wall tension with autoregulation and outcome parameters using a large cohort of patients post-head injury. So here, for assessing autoregulation, two methods were used, one being statistical one, which is the MX, which shows the relationship between changes of flow velocity and cerebral perfusion pressure, and the other one being ARI. ARI is a relatively new model-based assessment of autoregulation, and it's based on impulse response, changes between flow velocity and blood pressure. So overall, wall tension was inversely correlated to MX, meaning that increased MX, or impaired regulation, is actually associated with a decreased wall tension. So it means that the vessels are dilated, okay, and they lose the pressure reactivity. They lose their ability to react to changes. That's why the regulation is impaired. And this was also confirmed with the second index, ARI. But however, no relationship could be established between CRCP and autoregulation, this kind of cohort. We'll see later why. In terms of demographics, there was no relationship of wall tension and CRCP with age. There was no significant difference for these two parameters between Glasgow outcome scales. Okay? So assessing favorable or unfavorable or fatal, non-fatal patients. However, the ratio of wall tension to CRCP was found to be significantly lower in cases of unfavorable outcome. So this introduced a little bit on the concept of the role of vasoparalysis in worse outcomes. The role of wall tension in this kind of outcomes has less effect on CRCP because supposedly you have paralyzed vessels, dilated vessels, which cannot react to changes. Then I'm going to very briefly mention how I used CRCP for a non-invasive estimator of cerebral perfusion pressure. Danilo mentioned that before in his presentation, so I'm going to be very quick. So this is the model that is based on CRCP, and the important thing here is that it's based on physiological parameters, right? So it's based on cerebrovascular resistance, compliance, and heart rate. So it's not just a statistic model, right? It takes under consideration physiology. So in terms of comparison of the estimated perfusion pressure, ECPP to measured perfusion pressure, so you have a very strong correlation between invasive and non-invasive methodology, and you could also have a small bias of 4 millimeters of mercury. Again, we're talking about perfusion pressure here, with a standard deviation of 6. And this was shown, these results was also shown when you're estimating and assessing the group as a cohort of recordings. So the results here indicate patients. So it's bullets, it's one patient, average for the whole duration of their hospitalization. Okay, and the same was shown with recordings. The important key message to keep from here is that over 83.3% of cases had an absolute error of less than 10 millimeters of mercury. Now in terms of prediction, so how this estimated perfusion pressure model can predict low perfusion pressure, the results were very good. So I had a 3-row curve analysis, and I present to you here 2 thresholds, so for 15 millimeters of mercury and 70 millimeters of mercury. So these thresholds are generally denoted as a threshold for low perfusion pressure in the guidelines. And you would see that the estimation method had a very good accuracy, both for 50 and both for 70 millimeters of mercury. So what does this mean? It means that it's very good for estimating and detecting a low perfusion pressure non-invasively, right? So we're not talking about estimation, we're talking about non-invasively predicting a low perfusion pressure. Then we go to subarachnoid hemorrhage and cerebral vasospasm. So cerebral vasospasm is one of the most important complications following subarachnoid hemorrhage. Okay, what it really is, it is that you have a significant spasm, or you have a significant decrease in the vessel's diameter with this vasospasm, which means that it can impair and impede blood flow. Okay, so it can lead to a delayed cerebral ischemia. We can have significant results to the outcome of the patient. So what I did here, I examined the behavior of CRCP during cerebrovascular vasospasm and examined also its relationship to autoregulation. So the main findings for CRCP is that CRCP became significantly lower during cerebral vasospasm. So there has been a lot of confusion in the bibliography about what CRCP actually refers to. Many people were saying, you have vasospasm, you have restriction of vessel, you have increased vasomotor tone, so CRCP should increase. Well, this is wrong, because CRCP refers to the cerebral microvasculature. We're talking about small vessels. And these have an effect on CRCP based on the wall tension parameter. So CRCP was shown to become significantly lower, supposedly meaning that you have the small vessels around the spastic one being dilated, trying to compensate distally for that decrease in cerebral blood flow. And I'm saying that based on finding that ICP in the cranial pressure did not change significantly during the phenomenon of cerebral vasospasm. That means that if CRCP is the sum of ICP plus wall tension and ICP is fixed, it's static, every change that you see in CRCP, closing pressure, reflects the changes in wall tension. In terms of bilateral comparison, so before the occurrence of vasospasm, there was no significant interhemispheric difference for CRCP. However, once you have vasospasm occurring, so normally at 6 days average after the occurrence of subarachnoid hemorrhage, you would see that both the level, it's not showing here, but you could see that both the level of clear-closing pressure overall is being decreased, as indicated here, but most importantly, vasospasm induced asymmetry. Okay, so it means that the ipsilateral hemisphere, so the hemisphere where vasospasm was present, was shown to have a lower clear-closing pressure. Okay, so it potentially means, again, that you have a bigger vasodilation of the peripheral macrovasculature compensating for the spasm in that hemisphere. But also, the other hemisphere as well shows this kind of dilation, this kind of behavior. So, CRCP and autoregulation. So, if you remember, on TBI cases, we discussed that there was no relationship between clear closing pressure and autoregulation. Well, there was a relationship found here in subarachnoid hemorrhage, and it was an inverse one. Okay, so it means that you have high impaired regulation being linked to a lower CRCP, a lower critical closing pressure. I'm going to discuss later what does this mean. During CVS, so once vasospasm has occurred, this relationship becomes lost. So it shows you how important is vasospasm in terms of regulation of blood flow. So let's go in comparison between the different pathologies that I presented to you. So I wanted to note about the relationship between CRCP and autoregulation in TBI cases and subarachnoid hemorrhage. There was no relationship, as I mentioned just earlier, in TBI, but there was an inverse relationship in SAH. So one of the factors that affected this relationship is actually intracranial pressure, okay, which in TBI cases, it has been observed to be at higher levels in comparison to subarachnoid hemorrhage. So you could see around 18 millimeters of mercury versus around 13. So if you see again that the CRCP is a sum of ICP plus wall tension, it means that ICP significantly affects CRCP in normal circumstances. Marked changes could be only reflected in CRCP when you have low intracranial pressure. Okay, so my hypothesis here is that the vascular tone in both situations is inversely correlated to autoregulation, so dilated vessels being associated with the vasoparalysis and autoregulation impairment. But in the TBI case, this, because you have had a high ICP, this could not be shown. So there was no relationship with critical closing pressure and autoregulation. And this is one of the final slides. And here I'm going into more detail about which affects CRCP more. Is it ICP or wall tension? So again, I utilized the ratio of wall tension to CRCP, and I used the big cohort of patients that we had in Cambridge over the years to plot this ratio to ICP. And what you can see is that this ratio decreases with increasing levels of ICP. So it means that after you go, once you are below this line, so the ratio is below 0.05, it is when ICP plays the significant role in determining changes in critical closing pressure. And using a classification decision tree, we found out that you could have a limit of 20 millimeters of mercury for intracranial pressure. What does this mean? It means that if ICP is over that, then it dictates the changes in CRCP. Whereas if it is below that, changes in CRCP are dictated by the wall tension role. And think about that. So if you have a non-invasive assessment of critical closing pressure, and you have a non-invasive assessment of ICP through Professor Mascarenhas' methodology, and you know that you are below 20 millimeters of mercury, every change that you're going to see in critical closing pressure will indicate you what the vessels are doing, okay, in the brain. And this can be very important in terms of assessment of their status, and also assessing whether a treatment that you might implement works or not, whether it makes them dilated or constricted. So the key message to take home is that CRCP was estimated using the complex mathematical model, which takes account of physiological parameters in contrast to the previous methodologies. It eliminated negative values of past methodologies, bringing CRCP again as a reliable concept that you can work with in clinical reality. Then, based on the maneuvers that we saw, CRCP was found to be significantly affected by hypotension, arterial hypotension, intracranial hypertension, and occurrence of vasospasm. We used CRCP to explain the disappearance of diastolic blood flow and trying to give interpretation of this significant clinical phenomenon. And we also used the CRCP to form the basis of a new methodology which demonstrated promising results in regards to non-invasive estimation of perfusion pressure, most importantly, non-invasive prediction of a low perfusion pressure. And with that, I'm going into acknowledgements, and I would like to thank specifically everybody, of course, in my brain physics group. You can see all of my collaborators here, and especially my supervisor, Professor Marek Czosnica, which is also supervisor of Danilo Kardim. I thank all of you for your attention, and you're very welcome to come to Cambridge and visit us. This is my email, and this is my LinkedIn if you want to connect with me. Thank you.
Thank you. George, for interesting talk. Is there any question from the audience? No? Let me ask you a question. When you have these CPP-oriented treatment in the bedside during trauma, how do you compare your numbers with the 60 millimeters of mercury magic number that neurosurgeons use in the...
Yeah, so this study that I presented has been the basis. It's a foundation. It's the first study that introduced the new methodology. And this field is open for future research and collaboration in all of you. So I think this is one of the next steps that someone could utilize in order to understand. But if you know about the concept of optimized perfusion pressure, so theoretically, what you could do is to have non-invasive assessment of perfusion pressure and having optimized it without even putting almost a needle on the patient.
The other question I have is following. Have you investigated people with atherosclerosis to see about the wall tension changes because of this effect in the arterial compliance?
No, we didn't, but supposedly. So in arteriosclerosis, the vessel will have some kind of situation of, and this is a hypothesis, right, because I haven't worked on that, it will be severely impaired in terms of changes. So it won't be able to accommodate for changes in blood flow. So I haven't looked at it, but I assume that wall tension will not be able to change so much because the wall tension parameter that is presented here is active vasomotor tone. Okay, so because of the arteriosclerosis, you won't be able to do these changes in the diameter. But this is hypothesis, right?
Any other questions from the audience? Celeste, would you like to say something about this matter?
Yeah, well, I saw the application in the critical ICU of this concept of the critical closing pressure. I think it's really an important use to avoid the closing of the vessels, because otherwise we'll go through brain death. For clinicians, the problem is that this is not a continuous evaluation, so it is a sample that you get, and you may not be able to detect the exact moment when the patient has a problem. So we'll need to go further and try to have continuous monitoring possibility rather than a look only like a photo in time. Even if it is once daily, it's not the problem of that the patients have dynamics, and so you cannot detect the dynamics of the patient.
I would like to take the opportunity to mention, that this is all about monitoring, right, and the importance of monitoring, because a patient is not there, for 5 minutes. You measure, you go away, you look at the data, and you analyze the next day. The patient is always there, right, and have changes in the cerebral hemodynamics. So we are restricted in terms of technology. So here, as correctly Celeste mentioned, it's all about Doppler. So how can you have continuous Doppler assessments in terms of blood flow? Because you can put the Doppler for 4 or 5 hours, but then, you may have, treatments, so the patient needs to go to an MRI scan. Okay, so you need to take out the Doppler measurement, stop. Okay, or you cannot fix it to the head. So these are limitations that needs to be considered.
Tom, do you have any?
In your TCD examinations, did you ever observe reverse flow?
In patients?
Yeah.
No.
No.
Which is good.
Sorry?
Which is good.
Which is good. Yeah. No, I was just wondering whether the samples that you showed, the diastolic CBFV cut off at 0,
yeah.
And I was just wondering whether that was because the ICM Plus software didn't show you reverse flow, or whether that was actually 0 flow, forward flow.
Well, so you would think of it like, okay, so if the vessel has closed, okay, you have blood flow coming distally to that point where it's closed, right? So theoretically, this flow go back. So you would see both zero once it's closed, but also, backflow into that. But again, these were rabbits, right? We never saw that in patients in any of my 3 years in campus, so which is good in terms of management.
Any other questions? Well, thank you so much for your
Thank you. Obrigado.
nice talk. Now we have talk by Celeste Dias, Professor Celeste Dias from Porto, and I cannot refrain to tell you the importance of Celeste to us. She started us, connecting us to all these problems. We are very grateful to you, Celeste. So besides being a very important researcher in this area, she has received our team there with two of our main researchers. Spent almost a month in Porto, and we are very grateful to you, Celeste. By the way, your PhD thesis, I'm copying it and distributing it to the neurosurgeons here in the intensive care area because it's really very important. Thank you.
specific to the engineering area part, and using wavelength image or with a wavelength. And for that, we have in the market field several equipment that use different technologies and different wavelengths, all when intending to measure the difference between the external reading and the reading reading, and so respect photon and atomic reading, and also respect the relationship with the blood volume. So with regards to this equipment, and we use the phonometric equipment, so it's Julho, and with this we get the regional saturation, as you can see here, in the right side of the brain, and we can apply patients with a critical lesion, and we know that these patients are bounded to secondary brain injury, either due to increase in intracranial pressure or to decrease in fluid inertia, due to swelling, to also to some extracranial osmosis, and also due to problems with the autoregulation. And in the morning, when someone wakes up from such intracranial pressure is very important, that we fix the thyroider, because after the fixed thyroider is the external vital critical activity. And the clinician always has that autoregulation assessment at bedside, particularly for patients also with patients with so CT depends on the total hemoglobin content and saturation, density and pressure, also the total vesicule activity, namely the variation of CO2, the variance between the arterial and venous compartments, and CT is very important because when we are talking about the movement saturation, we are showing now the mixture of the individual in these two compartments. And one of the tricks of this technology is that we want to measure the blood component of the brain and that of the external part of the skull. And this may be a problem regarding the situation. And so it depends also on the thickness of the tissue below the skull, and this technology is also proven. Again, people are referred for overfeeding, and because we have local measurement of access to the blood, and also we have to know the definitive indication of the necessary fluid when we are talking about this rare condition. And we try to formulate that with also the standard depth. Those standard depth values are less than 50%, so we say that below 50% we have retinal, and about 75% we have rigid, and above 15% we will say that it's very good. For relating to the issue or representation of the blood pressure conducted with blood flow, so we may monitor in the frontal part of the skull the anterior arterial artery, and we also related the blood flow, we have reviewed the anterior arterial artery, so in the temporal part of the skull, and this research has a hair or represented by the hair, can apply the images to the distal part or to the ventral part, and we do have the images to anesthesia for monitoring this very depth. We monitor to the temporal relation to the total depth of the skull. So the application, human figure in cardiac surgery, and even though it's doing a hereditary population, we know that maybe it's important information that we get from the figure activity related to decreasing fluid pressure, and this may help to control the machine associated to the pump. Also, the imperative endoscopy may help to decide between the chance to surgery or not. During vascular treatment phase, so that we can stimulate important to see this intracerebral pressure. And after that, there is a use indeed in regional saturation, maybe due to hyperemia, but in some patients we could also consider not as a case. Some patients have not physiological measurement. At the same time, in most of the patients that we have, we could also document that with an increase the hyperemic value after the plasma. And here you can see the evaluation of autoregulation with three different literature with TRX, and the correlation between cerebral pressure, and we see that there is a positive value for the correlation between the autoregulation and there. And when we just going to look at the regional cerebral activity and calculate with the cellular correlation, we also see an increase of positive value for really good anti-CMI. So the same PK for the autoregulation are the usual equations in participants of the non-invasive method, in this case ACE. And here the work by the Steiner, when it could see that each program for using years as possibility of evaluation of evaluation may be applied also to other programs, to training programs, which affect indirectly the brain, hypothetical and extensive effects. So if we saw good correlation between the two possibilities of evaluation of the regulation with the software, ECG, and with also severe CMI. Here are some of the results with autoregulation experiments, so CBT evaluation, and indeed autoregulation may increase the severe safety effects. Also here we use a natural time domain analysis, but with a frequency domain analysis. You can see that when the unilateral pressure is changing, you see the same changes in this pressure. So there is a positive correlation, and here with baseline penetration, we also detect long periods of impairment of autoregulation. And we also try to estimate the optimal cerebral perfusion pressure using the method with the TRX. So we use the airbrush graphs, just plotting the CPT and the TRX values, and you have the minimum of this U-shaped curve being evaluating the optimal CPT, and you apply the same concept using different estimators for the optimal cerebral perfusion pressure. In this case, with the oxygen reactivity, so with brain tissue oxygenation. This one with the cerebral affinity, so with the near infrared light, and this one with the neurological measurements directly with thermal diffusion flow. And as you can see, there are different values for the optimal cerebral diffusion pressure values, which show us, like in my indication, that we are measuring different dimensions with different time response and also with different physiological response, and that's why we get different cerebral diffusion pressure, whether we are just trying to optimize only pressure or oxygen delivery or oxygen consumption or the blood flow. And we could also test looking at these different values and these different estimators of autoregulation, test the one that has the best correlation and also the lowest bias when we compare checking the fluid diffusion pressure, the optimal value according to TRX with the other way of calculating it. But the top estimator, which using years, was the one that has the lowest value, is 0.9 milliliters of oxygen compared to the last. Here you can also see another application of the cerebral oxymetry and look at the effect of CO2 in the brain flow, cerebral flow. So you can see just decrease in side of CO2. So when you take the increase CO2 away, you'll see decrease in different pressures due to vasoconstriction and a difference in the region and the consumption of oxygen in the brain and also some kind of affinity. So this is a patient with a different response either in the right or left side of the brain. Another application here also showing you how the effect of hyperventilation during an active crisis. This is somewhat a very important tool, although also a tool that we have to take into account because we are increasing the risk of ischemia and also what happens before and after hemicolectomy to the renal system. This is a technology that does not have content for all evaluations that we can take, and this is only an example of a lot of examples that we can get in the literature of consulting information. So these are two papers published in the same year, 2008, addressing the same topic, cerebral vagal stress, only using small samples, and one says that it's good, the use of cerebral oximetry to detect the effect of vagal spasm, and the other papers use exactly the contrary. They want useful in using it to detect cerebral vagal stress. Of course, we could just say that this may be a problem of the technology, or this may be a problem of the sample, or also this may be a problem of different territories that we are taking into account in the position of the oximeter. You also can apply cerebral oximetry to stroke, and in some cases you can, with other, for example, with other information, treat the decision for hemicolectomy. Also during cardiopulmonary arrest and for global fibromyalgia and during cardiopulmonary resuscitation, we can evaluate the quality of the resuscitation. And so this paper was published recently in the Journal of Anesthesia, saying that we may be a reliable marker that CPR can be defined early in the diagnosis of cerebral fibromyalgia. What we see in the clinical field is that the brain oximeter is faster, has a faster response compared with the physical oximeter. Here is one of the papers mentioned there with the decrease of the brain oximetry during cardiac arrest and then the required oxygen infusion. Also during ECMO, so the extracorporeal oxygenation, of course we are very concerned about the brain oxygenation during this program to have CRPA. And here, as a non-invasive method for these patients, we also have to target the oxygenation and the CO2 removal from these patients. And here you can see a good correlation between PbCO2 years and also the saturation with a good correlation during extracerebral membrane oxygenation. Another technique is appearing in the market that joins two technologies hearing for later life, and ultrasound, as you can see here. And with this, maybe you can also add to the explanation of oximetry or brain oximetry, the direct measurement of cerebral blood flow that will allow us to really, with continuous monitoring, to have assessment of these two important parameters. So we'll have serum metabolic rate and serum blood flow. So here is the technology, I think, needs further development. We need better oximeters, also better algorithms. Another important issue that I, as a clinician, think that we need is also a fitness algorithm using, so how can we teach the young doctors how to give value to the changes that we get, and what are the main causes for the differences that we get from the patient, and how to decide to treat them, and maybe with education in functional offer will get further information with more feasibility and reliability. And this is the last slide, and I thank you for your attention, with the plateau rate and the regional saturation from the left and the right side of the brain with this is real zero. Thank you.
Thank you very much for this talk. This is very important for Brazil because we have some groups already working in that at the University of Campinas, and they have done several contributions. You are going to meet them in São Carlos on the 15th, and I have some questions about the use of when you look at the cost of this for us in developing countries. Is one question. The average price of the instrument you use is in which order, more or less?
Well, the consumables for in Europe or in my hospital are about 100 euro for the oximeter. But I don't know what will be the price in Brazil, because I know that, for instance, and probably you may not know, intracranial pressure sensor for Cosman costs in my country about 500 euros, and here the comparison is 3 times more. So here in Brazil, so it's really not only a problem of the cost or the real value of the price, but also the cost that of difference between the health systems that generate different prices in the world.
The other question I have, when you compare, I read some papers in which people are trying to use NIRS as a cognitive type of instrument, comparing it to MRI, functional MRI. Do you have any information about functional NIRS?
No, we don't have this information, and mostly the information about cognitive assessment is nice. It's for multiple detectors. So we are not using that technology. We are using a simple technology. But I don't know if we can just relate some of the problems that we have thanks to the critical care patients, the huge or massive use of sedation with huge decrease in metabolic cerebral rate, may cause some impairment also in autoregulation, and may cause some impairment in the synaptic physiology that in the future will lead to cognitive impairment. And I don't know if the near evaluation can give us an answer to that. Also, if the EEG monitoring during deep sedation will help us. But I think that we need to study more and to have more clinical data so that we can relate, because we know that deep sedation has patients that have deeper sedation during intensive care have higher mortality. So if this is related then to cognitive impairment, we may think that that is true, but we have to see.
Any questions from the audience? Yes, please.
Information about the flow waves from the nearest signal and relate that to that regulation, more than the absolute value or the trend value for the regional saturation. It's the study and the research of this technology and non-invasive methods for testing of auto-regulation.
It's very interesting the use of NIRS to do the CPP optimum. And I'd like to know if you think that oximetry can be used as a new method, a new input to calc the non-invasive intracranial pressure like arterial blood pressure, or a new mathematical index to put in the algorithm.
Questions? Then I have a last question. When I first read about NIRS, since I had worked before in photoacoustic spectroscopy, I thought that would be a good combination to use photoacoustic spectroscopy together with NIRS. Then, of course, I was surprised and sad when I saw several papers using photoacoustic spectroscopy together with NIRS. Now that would be important because photoacoustic spectroscopy gives you thermodynamic information and elastic properties information too. Have you been in contact with these people that use photoacoustic spectroscopy?
Another important information that we get from that, or that we may get from that technology is also the depth that we are getting of the tissue. So we increase the certainty of getting information from real cerebral blood flow rather than external or extracranial.
Yeah, because what I see that you might get things like temperature information, which is extremely important to evaluate the oximetry because it depends on the temperature. And the other thing is related to the elastic properties of the medium, compliance and things like that. So if you could couple the photoacoustic spectroscopy that gives you all these other thermodynamic parameters together with the That's
That may be related to edema that will be good. The amount of water that increases tissue and the relation with this thermodynamic properties.
And also the epithelial properties of the vascular system that compound the complications of the... Well, thank you. Any other question? Thank you very much, Celeste. Now we have the pleasure to hear Professor Duarte, who is the head of the gynecology and department here. It's a very illustrious researcher in Brazil, was director of the Children's Hospital in our medical school, and is completely dedicated to research and of a series of health problems in Brazil. We are very grateful to him to support collaboration with our group, trying to understand something on ICP and preeclampsia. And thank you very much for coming.
Good afternoon, everyone. Too weak. Good afternoon. After their lunch, it's not easy to have class talks and lectures. It's not easy. But, Sergio, thank you for having me here today. I learned a lot this morning and begin this afternoon. Thank you for this huge opportunity to learn and to talk about one nightmare. I will give you an overview about preeclampsia. Overview and deep on some topics that we think is more interesting for these people. That these people here, it's very deep, hard science in neurology and physics and mathematics. And then I will give a little more deep in this topic. I think is more interesting for you. But let's work. This title is really not dream. This title is a nightmare because this is a big problem we have in Brazil. And I will try to show you this for you in this 30 minutes. This agenda, I will try to give you some information about the classification of hypertension syndrome during pregnancy, preeclampsia, pathophysiology, diagnosis and treatment, mortality and morbidity, the Millennium Development Goals, and some links of preeclampsia with brain blood flow. The classification of preeclampsia. Preeclampsia, we grow up hearing our grandmother, grandfather, and mothers saying preeclampsia, hypertension, chronic hypertension. But what is this? What does it mean? We have 4 types of hypertension during pregnancy, and then every type has one particular aspect. Chronic hypertension. The woman has hypertensive syndrome during before the pregnancy. Gestational hypertension, no hypertension before the pregnancy, but get hypertensive syndrome. Preeclampsia. Preeclampsia, we have some details that will go forward with you. Preeclampsia and eclampsia, with the difference about those. And chronic hypertension plus preeclampsia, eclampsia. The first condition with the third condition. And then more severe clinical feature. What's preeclampsia? It's a systemic disease. It's not a disease of the fetus, it's not a disease on the uterus, no, it's a systemic disease. Second, half on pregnancy. Unknown etiology in prophylaxis, and then is difficult. If I don't know the etiology, how I can treat correctly is very difficult. But we know that the problem is based on endothelial dysfunction that can affect the several organs, and high rates of maternal and perinatal mortality and morbidity. And this I need to go deep with you. Endothelial dysfunction is the fundamental stone of this disease. But the interrogation dot is why? Why the woman get this dysfunction, endothelial dysfunction? This is the big problem, and sure, we will have Nobel Prize for the people or researchers that discovered this. The problem of the forward, more than poor people. And then we have the color more strong with the people, the poor people. But what's so clear in Africa? Because they don't have registries. They don't have numbers to talk about. And then, but with the country that they have some kind of information, we have the poor people, they have the most high incidence of this disease. The world, higher incidence during winter time. The winter time is terrible for preeclampsia. Now, it's the winter here, but it's not so cold. But we have all our beds there in the hospital are full of this people. It's a disease of the winter. And several countries are without reliable records, as I said this before. In Brazil, these numbers is for in the beginning of the decade. And now the Brazil data of 1913, the hypertension, the incidence was 10 to 12%, and preeclampsia about 5%. What is the hypothesis for preeclampsia? See, if I don't have one etiology, definitive etiology, pneumonia, I have one bacteria, but preeclampsia we don't have. And then if we don't have a name for this etiology, I have hypotheses, and then I have several hypotheses. And then superficial trophoblast invasion is one possibility. Inadequate remodeling of uterine spiral arteries is another. Endothelial dysfunction is, we can find this, but I don't know why. Immunologic factors, genetic factors, and inflammatory factors. All these are a huge chapter in the medicine. How I can explain the problem with endothelial dysfunction and the etiology goes to further we can. Here we have the umbilical cord, two umbilical arteries, and one umbilical vein. They divide and it goes to the intervillous space, and we have here, we have this exchange of the oxygen and some CO2 is in this part of the placenta. The mother vessels, they have arterial and venous, and the spiral arteries, they through the blood in this intervillous space. In this intervillous space, we have the exchange of the blood elements, maternal blood elements, and fetal blood elements. In this part, we have the exchange of this. In this unity, little unity, we have the fetus has your life, his life. When you make this a cut here, we can see the vessels, the fetal vessels, and when this little layer here, this is citrotrophoblasto, here and continues here, and goes to the placental part, maternal placental part. And in this part here, the cytotrophoblast will invade the spiral arteries. The spiral arteries is microscopic, almost microscopic. And then with this invasion, these arteries is enlarged and can throw out more blood for this fetus. Because the fetus, he grows, and needs more and more and more elements for his growth. And then needs more blood. Then this process, the invasion of the spiral arteries, doing by cytotrophoblast, makes this. Here we have the result. No pregnant, normal pregnant women, the invasion, and this is very large phase. And here is with preeclampsia. The preeclampsia, this process does not work. This process failed. And then we have one hypoxia. In all this tissue here, we have hypoxia. With hypoxia, it is different. If I am stay in a good nutrition, my body, my responsive bodies will be the normal. But if I have problems with nutrition, it will be different. For the placenta and the vessels, the systemic vessels is the same. The fetus is the same. This fetus here, today, has problems with nutrition. We need to think about the future. They are the people with hypertension in the future. They have obesity in the future. And then we have all this. Preeclampsia is not bad only for mothers. It's bad for fetus, for children too, and adults. Here was an example. You have the invasion of the veins here, the spiral artery, and then you can see the projection, the comparison of these veins. And this unity, placental unity, are a real laboratory. And with all the substance can be synthesized. And some are specific of this. And then you have all these markers for good works of this placenta or bad works of this placenta. If this placenta is well with good nutrition, the secretion of these markers will be normal. But if this nutrition was not good, these markers here will be unregulated, and then we will have problems. And then we have aggression for this endothelium. And with the aggression, we have dysfunction. And then we know the process. We don't know why. Continuous, we don't know why. When we give the medical degree for Dr. Sérgio Mascarenhas, some time ago, long time ago, the preeclampsia was the definition of preeclampsia. It's three variables together. Edema, proteinuria, is protein in the urine, and hypertension. This is old because we have some progress. Edema, all the pregnant women have edema. So one day with hard work, have edema. It's not good, not helps. And then consider today hypertension and proteinuria. Who is considering this? WHO and Royal College of Obstetricians and Gynecologists. They consider hypertension and proteinuria in these levels here. But everybody in the world consider this? No. The United States, no. American College of Obstetricians and Gynecology say, no, preeclampsia is only blood pressure above more than 14 and 19. The systolic and diastolic millimeters of mercury. And with hypertension, this level, and one of this alteration here. And then it's a part of that old concept of one kit of hypertension, of preeclampsia, and more dynamic, because we have some alteration of the health of this pregnant woman. And then I think all the classifications are good. The problem is care, adequately care. And you know this is not easy. Moderate preeclampsia. Oh, and then you know what we're talking about. Yeah. But, when I say that preeclampsia is a disease of all the body, the eyes will have vasospasm, edema, kidney proteinuria, oliguria. Oliguria is low flux of urine, low volume. Edema, hemorrhage, headache, cycle problems in the brain, placenta, infarto, fetal hypoxia, and a restrição de crescimento, factor restriction de crescimento. The fetus don't develop adequately, and coagulation we have activation. All this is based on arterial spasm. This arterial spasm, this answer of these injuries of this endothelium is very problematic. Severe preeclampsia, we have severe headache, problems with vision such as blurring or flashing, severe pain epigastric, just below the ribs, vomiting, sudden swelling of the face, hands or feet, and severe psychological problems. And then here we have some helps with the people, image people. This group has at least 5 papers, very interesting papers, studying the pressure in the flow, the blood flow inside the brain of this women. And they compared. Here we have the variation, the systemic variation of the blood pressure, and the variation here with the flow of this blood in the cerebrum. In the cerebrum, the pressure of the blood pressure is very high. The vases, the arteries, they work in a very high resistance, and controlled by CO2. And then when you have the systemic with blood pressure low, we have a dilation, vasodilation, cerebral vasodilation. Why? Because the interpretation of the cerebral is, we don't have enough blood. We need to vasodilation to have more blood. And then we have this in the normal women. But in preeclampsia, we don't have this answer adequately. And then this clearly contributes for the hypoxia for this in the cerebral of these women with preeclampsia. And here is one summary of this. Here, one paper from this group, they manobra de Valsalva's maneuver is don't breathe for 15 seconds. And then we have some hypoxia. And then the hypoxia, we have heart rate. I have below for this, but the preeclampsia is not so intense. It's not normal, the answer. We have in this here with a better figure. We have the normal, and then we have preeclampsia. The resistance of this vase, the middle artery, we don't have the answer with the normal and the preeclampsia. And then shows clearly that some stimulus that cause hypoxia, we have problems with this. We don't have the adaptation of this cerebral arteries. And then preeclampsia and danger, very dangerous for the cerebral. The severe preeclampsia, we have more problems. The eyes, we have scotomas, blurred vision, and blindness. Sometimes we have blindness. Two kinds of blindness. Blind for detachment of the retina, here, it's very problematic, and cortical blindness. This we can revert, but this is very difficult. We have the kidney, oliguria, proteinuria, reduced kidney function, cycle problems, vomit, hemorrhage. Micro, more micro, becomes macro hemorrhage. And then is the main cause of death of this women. In the placenta we have infarto, restriction of growth, and fetal death. And coagulation is we have activation, we have problem. And then we have the real nightmare in this position. We have seizure. Seizure is convulsion. The same. With this, we have more problems with blindness, cortical blindness. We have seizures. With seizures, we have eclampsia. It's not anymore pre-eclampsia. With seizures, we have eclampsia. The name changed. And we have other complications. It's not only seizure, it's not only eclampsia. We have HELP syndrome. HELP syndrome is when pre-eclampsia has alteration in the liver, stasis, epigastric pain, enzymes, and hematoma with possibility of rupture. And hematologic system will have hemolysis, thrombocytopenia, and hemoconcentration. And then we call this HELP syndrome. It's like help, but help, the word help has one L. Elevated liver, enzymes liver, low platelet, and hemolysis. It's the acronyms of all these alterations here. HELP syndrome. The last women we lose was in the beginning of this weekend. One woman that were carried in another city and comes to our hospital with HELP syndrome, stay in the hospital for 5 hours and died. The last one, the last weekend we had. But in the summary, we can say HELP syndrome is when we have this alteration here with hypertension, proteinuria, we have preeclampsia. This feature, clinical feature, is HELP syndrome. And when we have seizure, we have eclampsia. It's okay? Go ahead. Well, how I can do this diagnosis? How the lab can help me? I don't want to teach about the diagnosis. I want only show you that this disease is terrible, very expensive. Not only expensive for money, expensive for families. You have idea, one child with mother. It's terrible. For our society, the mother is very, very, very important. Father, we can reaggregate. Mother, the lack of mother is very dangerous for the family. And then the price for preeclampsia is very high, not only for financial costs. We can treat preeclampsia? No. I don't have the etiology factor. And then we control. We control preeclampsia. But we know something. The trophoblast is the villain. The effective treatment is the interruption of the pregnancy. If I put out the placenta, I have the problem solved. Okay? But it's not all the patients. We have prematurity. We have preeclampsia in 24 weeks of gestation. And then we cannot interrupt the pregnancy in this gestational age. Lack of an animal model to study. And then all the treatment are, until now, only control. How is the drugs we can use? A lot of. Neither is good. Methyldopa, nifedipine, pindolol, atenolol, all this. And no, never use diuretics, hydralazine, oral hydralazine, and the inhibitors of angiotensin converting enzyme. Why? This worsens hypertension. This, we have tachyphylaxis, and angiotensin converting enzyme inhibitors, we have fetal death. And then we need to be careful with this. This one, fluxogram, but I would like to stay here. We can use hypotensive drugs, magnesium sulfate, and exception drug. Hypotensive drugs, we can use hydralazine, this in decreases. Hydralazine is intravenous, labetalol, and nifedipine. We can use this, nifedipine is sublingual. Exception drug, sodium nitroprusside, is only for very severe cases we can use. And then our choice is hydralazine or magnesium sulfate. Magnesium sulfate is the drug you use more in all the world, is magnesium sulfate. Protection of maternal CNS, protection of fetal CNS. I was talking with Thomas before, this morning. Elective drug for severe preeclampsia and prevent eclampsia. Elective drug for eclampsia too. Okay. Magnesium sulfate is good. But we have this little banner in the room of the nurse. The nurse has one place, one room to prepare the medication. And then there we have this in Portuguese. The warning. The care with these people when we decide, oh, I will give for these pregnant women, I will give magnesium sulfate. And then we need to decide and to be careful to select. this topic is hot. But then I was talking about the carefully. We need to be in the selection of the patient and with nurses doing the correct dilution of this medication, and when they will give the infusion. Because, I don't know if you can see here, maybe in English is better. The therapeutic level is 4 to 8 milligrams per deciliter. And then the patellar reflex loss is 9 to 12. And then it's very toxic. The dose, the pharmacological dose is close to the toxic dose. And then not all units can do this. We need to be very careful. Just in this medication that saves lives. And then it's very a big limitation, very difficult for us. Okay, we have the obstetrical, we have goals in our profession, in our specialization. We have 2 patients. We have the mother and we have the fetus. They pay only 1 visit, but it's not a problem. We have to have in mind to reduce perinatal risks and maternal risks. And then the preeclampsia has for fetus and neonatal, we call this perinatal period. We have high mortality and high morbidity. Perinatal and maternal. Okay, perinatal, what this disease can do for these babies? Hemorrhage, lung, brain, adrenal, and the heart. Fetal growth restriction, premature heat complication, low weight at birth, long stay neonatal UCI, and death. The main cause of perinatal death is hypertensive syndromes for us. Other countries has other statistics, but for us in Brazil is hypertensive disease. And for maternal death, the world, this data is very new, is hemorrhage more than hypertension. But in Brazil, it's a little different. The problem with the mortality, maternal mortality, is very difficult. And the OMS and all the institutions for health in the world, they create the Millennium Development Goals for 8 objectives. And the 5th goal is to improve maternal health. And then let's go to this Millennium Development Goals. For the world, they would like to reduce the maternal mortality for 45%. What happened in Brazil? Is for the world. For Brazil, was more, a little more. For Brazil, we would like to reduce this for 70%, 70%. And we would do only 43%. And then Brazil will not reach the objective of the Millennium Development Goal. We stayed in the end of the 2013 in 69%. In the end of the 2013. And then for 2015, our goal was 35%. And then in 2013, we have 43%. 69 is the same of 2008, and then we reduce in a good velocity here, but we stayed here, and then we have a big problem. And then we need to close all the knowledge in the world, Brazil, all the world, to find the way to reduce mortality, maternal mortality. Okay, in Brazil, it's different of the rest of the world. Hypertension is the leader, more than hemorrhage. Here, showing that hypertension in all the age groups, the hypertension kill more mothers. Well, screening is, for us, is the same as prediction, and prophylaxis is the same as prevention. Okay, can we do this? Okay, if I can treat, if I can do something, I need to know who is under risk. And then I have some hints here. Epidemiological indicators, serum markers, chemical laboratory dosages, and ultrasound, and maybe peak. It's a challenge for Dr. Sergio. And epidemiological indicators. All this condition has more risk for these women to get hypertensive syndrome. For this, here we have one evaluation to American people, one evaluation, chronic hypertension, pre-gestational diabetes, multiple gestation, pre-eclampsia, nulliparity is more frequent in this first pregnancy. And then all this we have adjusted odds ratio, we have more frequency about these people. And then more and more, we have a lot of science in this group. Serum markers. Serum markers, we have markers for oxidative stress hypoxia. Dr. Sergio has one collaborator here in the philosophy faculty that can do this in the rapid way, I think. For inflammatory markers, products of placentation, endothelial dysfunction. And then we have a lot of possibilities. These are marketed. We have in the market. The others we don't have yet. And ultrasound. Ultrasound, if in this age of pregnancy, I can measure the flow of the blood flow in the uterine arteries. And then when I have the pulsatility index more than 15%, 5%, we have, with the gestational age, more than 90%, 5%. More than this, we have the problem with this pregnancy in the future. We have a lot of risk for these women. And here we have one picture of this exam, the ultrasound. Here we have for the flux, the blood flow for the uterus needs to be very high. We cannot have any resistance. And then in the normal pregnancy, we have the diastole very high here. And then see what happened with the preeclampsia. The diastole is not so high. And then we have this, we call this incisura, or knot. In English, knot. It's a knot here. And then it's a problem. It's an indicative of hypoxia, indirect indicator. And then we can do this with in the beginning of the pregnancy and select the women that we will have. But we don't have the ultrasound for everybody. Can we do the prophylaxis of preeclampsia using aspirin? We have some problems because this not works for everybody, only for risk. If the patient are in risk, works, but it's not risk, that doesn't work. Aspirin doesn't work. It's a synthesis for you. Here is a way we have to show that it works, but works only in the selected groups, don't work for everybody. And calcium. We open the PubMed or one magazine, and you have calcium. Calcium will save the nation. But it's not so easy, because calcium we have only for low intake population. If you have problems with the intake, works. If not, doesn't work. And then don't save the nation. We have problems. And if you have then we'll put calcium for everybody in Africa. An example. We have problem because 1 or 2 grams a day. We have problem with the storage. We don't have where to put this in Africa. We tried, but didn't work. And magnesium sulfate intravenous for prevention of preeclampsia. It's possible. I think it's, but let's see what happens. Do you remember that? What? This. Now with hope, but it's dangerous. And then how I can put this medication like this in the unit, the basic unit of health? It's difficult. We don't have people enough prepared to do this infusion. And then it's difficult. It's difficult. Oh, but I can select better. Oh, it's not easy to select. Clinical feature is not specific enough. It's not. The blurry vision, scotomas. I have other condition that the patient can have this. Ultrasound does not measure pressure, intracerebral pressure, indirectly. But I can have the ultrasound device in the unit of health. It's difficult. And then a measure of intracranial pressure with a non-invasive way, with a device, a simple device, maybe could happen. And then this device needs to be of affordable price, easy to use, rapid results. Do the exam, and I need to have the result fastly. Online evaluation. Oh, I don't know how evaluate this result. And then put this in a cellular phone and send this data for a central. In the central of the diagnosis, I have somebody that will do the diagnosis of intracerebral pressure, elevate intracerebral pressure, and do all the orientation for that specific case. For using the basic unit of health either. Because all the new things in health, only for tertiary hospital, only for big hospitals. And then I have a big preoccupation. Sergio knows me well. I'm a fan of our SUS, the National System of Health. I'm a fan. It's the only way this country has for our health. It's not good, but it's the only we have. And then do medicine for the rich people is difficult, but it's easier than do medicine for poor people. And then if my fight is what the rich people has, the poor people needs to have too. And then this is the big challenge we have. Progress for Dr. Health, maybe not, for Celeste. Progress is this, one ultrasound of less type, less generation, but for poor people, clean water can be the progress. And then our challenge, Dr. Sergio, is not only do the best, and do the best for all, for poor people too. Thank you. Thank you.
It's good to hear about real problems when you look at all things in, when you model and you put in a computer or you present beautiful mathematical graphs. But this man here is talking about real problems in Brazil and in many other countries. So it's very good to hear practical things and real things. And besides here at the medical school, Professor Geraldo Duarte has an infirmary with dedicated beds. I think there are 27 beds just for risk pregnancy in this medical school, which is unique in Brazil because it's they are completely dedicated full time to this region, to these women in the region with risk pregnancy. So we thank you very much indeed for this talk, which is the
we are together in this fight.
And we have this challenge, UNESCO challenge for Brazil. We still did not get to the point where we should have decreased it by 75%, that's right. And we are still only at 63 or something.
43.
How much?
43. We reduced 43%.
I see.
We need to reduce for 35.
So it's a great challenge for us in Brazil that work in the health problem. And we are indebted to Professor Geraldo and his work for bringing this problem to our attention here, trying to include physicists, pharmaceuticals, physiotherapists in these interdisciplinary efforts. Thank you very much. Is there any questions?
The doors are closed, are open for everybody.
Any question from the audience? Professor Thomas?
Thank you very much for a great talk. It was very inspiring and also very informative for those of us who don't work with preeclampsia on a day-to-day basis. Maybe this is too naive to think about it. We have another syndrome where we have endothelial dysfunction, and it is very difficult to come up with a good animal model, and that is sepsis. And it almost seems to me that it's the complete opposite of sepsis, right? Where we have this massive vasodilation cascade that we have in sepsis to severe sepsis to septic shock. Here it seems that you have endothelial dysfunction, but on the opposite end of the spectrum. You actually have vasoconstriction, you have coagulation cascade being important. So I wonder whether you could comment on that notion, whether it's too simplistic to think about it, or whether there is something that one might want to consider. The second question that I have is, I noticed that India had a very low incidence of preeclampsia in the chart that you showed at the very beginning. It's a developing country. It has a very high incidence of blood pressure in of hypertension in the general population. I would just be interested to know if anyone knows why they actually have such a low incidence of preeclampsia, lower than Europe, it seems.
I will start for the easier answer. Is that I don't know why. The second question. We don't know why. We don't have one explanation for this. The first one is the problem with the sepsis is the inflammatory problem. Because the medication for bacteria we have, but when the inflammatory answer, the body answer, the inflammatory aspect, is very difficult. Why? When the problem starts, Celeste doesn't have one medication to stop it. One inflammation, one problem with my nail, inflammation, I have edema, pain, and then save my life because put in this box. But when this body answer, inflammatory body answer, is systemic, we have a syndrome. And this, in the beginning, the objective was to save my life. In the end, kill me. This is the big problem, the big difference. And for the hypertensive people, the HELP syndrome or seizures, eclampsia, we have some problems in the etiology with inflammatory markers that are very high. And then in some case, I think we have some influence of this inflammatory answer. But what kills these women is other things. It's something that goes to the brain and goes to the liver. This big problem for these two organs. Then I think, I don't know if I answered you globally. Yeah. Celeste.
I would like to do two comments. One is related to maybe some similarities in the anatomy, and the other is some kind of personal comment. So when I was just relooking to the anatomy of the spiral arteries and to trophoblast invasion, I remember of the Bischoff space and the subarachnoid hemorrhage and the problem of cerebral vasospasm when the blood invades that region of conflict between the vessels and the tissue. And here, I think that we have the same problem, the conflict between the vessels and the tissue. So the exposure of the tissue or the vessels or the blood to some tissue factors, maybe. And another problem is that we more than an intracranial pressure at the beginning, we have a problem of vascular reactivity, either in the uterus or in the brain or also in the kidney, because also kidney has problem. And then afterwards, then the liver will appear. But the first three organs are the uterus, the brain, and the kidney, or you may say the kidney and the brain. And when you just compare the anatomy of these three vasculature areas, we see that they have a special feature, that is high flow and low resistance. All of them, they are all similar, and they all share these properties. So I think that we should look at these conditions, and so that we may find a clue to the answer of the why it appears, the reason for the initial. So the personal comment is that when I was pregnant the first time, and I was in the 4th month of pregnancy, I just passed by through a colleague of mine. She's a gynecologist, and she said to me, "You have your face looks like eclamptic." But my blood pressure is normal. Yet, she said to me, and she was true. So also, what happens to the mother face that goes something like we are blowing something? I don't know. And then another comment that I discovered afterwards. So fortunately, I only had hypertension, and my child was a premature baby because you have to remove the placenta. And
you read the book.
Yeah, so yes, I read the book, but I read even further because I discovered that the stress, the oxidative stress that my child suffered in uterus will the problem will continue during life, because she developed the problems during adolescence, and I know that she will have more problems according to cerebral vascular problems in the future adult life, because we already know that. And this is the only cause is the exposure during fetal development to a high stress oxidative ambient. Okay.
Thank you very much. In the next meeting we have, she will talk about preeclampsia.
Yeah. We hope she will help us.
But we have a joke with the residents. When the patient comes in, all the clinical feature fitting exactly like the book we saw, we say, oh, this patient, read the book. Then everything is there.
Very good. Any other question? Well, I thank you very much for this beautiful talk, and you
thank you, my guru.
Great help to us. Now we have Dr. Mateus Balesteiro, who is a neuropediatric surgeon, and we have the pleasure to work with him at the neuropediatric infirmary here at the medical school in hydrocephalus, in pediatric hydrocephalus. He's going to talk to us about his results. Thank you very much, Mateus.
Thank you, Professor Sérgio. First of all, I would like to apologize because I didn't prepare my presentation in English. I will try to speak in English, but the slides are in Portuguese. I'm very happy to see old professors of mine, like Professor Geraldo. I don't know what happens, but he never gets old. And Professor Luisa too. Well, I will talk about non-invasive monitoring of intracranial pressure in children with hydrocephalus. It's part of my master degree project. That we developed with Professor Sérgio Mascarenhas and Dr. Gustavo. Just a minute. Okay. Well, a little talk about hydrocephalus. It's sometimes is difficult to get a full diagnostic of hydrocephalus. It's not quite easy. In some cases, we have an incidence of 4.6 to 5.9 per 10,000 birds in Brazil. This number is from Brazil. And the hospital cost of treatment of this patient is about $36,000 in US, with a cost to the public not to the private system of about $1 billion per year. In Brazil, we don't have this calculus, but this work from 2030 says that we spend like 50 millions reais in chance to treat hydrocephalus. So it's very expensive to Brazilian and to US service. And hydrocephalus has lots of causes. It can be congenital or acquired. Congenital hydrocephalus, it's mainly caused by myelomeningocele, and acquired for intraventricular hemorrhage of the premature children. But we have another causes like traumatic brain injury, or subarachnoid hemorrhage, or some deformation from the skull, like Crouzon syndrome or Pfeiffer syndrome. About the classification of hydrocephalus, we can classification in obstructive and communicant hydrocephalus. And the definition is quite difficult, but I think this is the best definition for hydrocephalus. It's a condition in which there is some blockage in the circulation of the CFS in some point, and in any moment this liquid, the CFS, accumulates, and you have some ventricular dilatation. It's a progressive process. Well, the CFS is produced in the choroid plexus. 90% is produced in choroid plexus. 10% in other points like ependymoid tissue, subarachnoid space, and we produce up to 500 mL per day, and the adult has about 120 mL of liquor, and this liquor is absorbed in the arachnoid velocities. Here you can see a picture of the liquor. It's produced here, and passed through the ventricles, and it's absorbed here in the venous sinus. If you have some obstruction in any point, it will cause hydrocephalus. So what causes hydrocephalus? What ultimately causes hydrocephalus? Or we produce more than we can absorb, or we can have some difficulty in absorbing what we produce. Or we will have some obstruction of the circulation in any point from the production to the absorption in the velocities. Right now, the diagnosis of hydrocephalus is based on clinical presentation. The patient, the children has headache, nausea, irritability, but in young children it's difficult to know exactly what the problem with the children. So we have to use some images, some complementary diagnosis, like ultrasonography, computed tomography, and MRI. Each of one has difficulties. Ultrasonography we can use it mainly in children below 2 years, because they have a fontanelle to access the ventricular systems. We cannot use in older children. CT produces radiation. It's a problem to radiate children. It's always a problem because of pro-oncologic effects. MRI is expensive and demands lots of time. It's difficult when you have a patient in mechanic ventilation or stuff like that. Because of that, it's always difficult to assess hydrocephalus in children with lots of surgeries when we operate the children lots of time, and when the student has the closed fontanelle. Well, and how we treat hydrocephalus? Hydrocephalus is treated mainly by surgical intervention. We have the shunts, as I said, that most of the time are very expensive. The shunts goes to the ventricular system, to the peritoneum, to the ventricular system, to the atrium, or to other places like pleura, venous sinus, ureter, femoral vein, biliary vesicle. This is about 80% of children are treated with this kind of shunt. 80 to 90%. Endoscopic ventriculostomy creates an alternative way to the FSR to circulate, but it's not usual to do this kind of surgery, and we do not have pharmacological ways to control hydrocephalus yet. So we treat hydrocephalus with surgery in up to 9% of the cases. Well, as the school is a closed system, as I think we talk about the Monroe-Kelly doctrine lots of times. No? Yes? So when you have some obstruction to the circulation of the liquor, the intracranial pressure has to get higher because the intracranial system is closed. So here is a classic curve of pressure volume of the school. When you put some volume like FSR liquor, we have some point that we cannot compensate this, and the ICP will rise, and this can be mortal to the patient. Well, and how can we know how's the intracranial pressure of this patient? Right now, we have to put some invasive sensors like intraventricular, intraparenchymatous, subdural, or epidural. Each of them has complications. But when we put the sensor, this is very important. The value of the intracranial pressure is not the most important thing we assess. We have to look to the intracranial pressure wave. We have lots of tips with these waves. Intracranial pressure has up to five waves, mainly P1, P2, and P3. And lots of works say that when the morphology is like this, P1 higher than P2 and P3, the brain's compensation, and probably the pressure is, the intracranial pressure is not so high. But when the intracranial pressure gets higher and higher, this difference is not so good, so important, and sometimes P2 can be even higher than P1, as I will show. Well, this is a slide from Dr. Mascarenhas saying that the Monroe-Kelly theory is not this Monroe-Kelly theory is not fixed. He puts a balloon in a cranial and try to measure the deformation of this cranium. As he puts more and more pressure in this balloon, he could measure the deformation of the skull. And when the pressure becomes low, again, the screw returns to the position. He measured this deformation with the eye strain gauge. Eye strain gauge is this piece of electrical system fixed in the screw, which we can measure the deformation of the screw. And as we could see here, it was possible in a dead screw with a balloon. But we have a work in progress with patients with traumatic brain injury. When we put this system called the minimally invasive system fixed on the screw, together with the invasive system, or intraventricular or intraparenchymatous, and we could see that both intracranial pressure waves, as I will show, are very similar. This is the minimally invasive system, the first invention. After that, we have the completely non-invasive system developed in 2013, and it's a coupled extension. I don't know if this is the name, but you don't need to put this or fix in the screw with a surgery. You only put in the screw and fix with this kind of dispositive, as you can see in leisure. So here we have a patient with traumatic brain injury, and we tested the three dispositive in this patient: an invasive dispositive, a minimally invasive dispositive fixed in the screw, and a non-invasive dispositive, and compress the jugular venous to when we do this kind of maneuver, the intracranial pressure gets higher. So when the jugular venous is free, the pressure is low. When you compress the jugular vein, both systems tend to show that the intracranial pressure is higher. When you liberate again, the three systems goes to the same point. This is another experiment with rats showing comparing the invasive system with the minimally invasive system. When the patient is, the rat, not the patient, not my patient, is resting, the intracranial pressure is in this point. When we elevate the posterior portion of the rat, the intracranial pressure gets higher because it's difficult to the blood to get out of the brain. So the intracranial pressure gets higher in both systems, invasive and minimally invasive system. And when you elevate the anterior portion of the rat, we do this with patients when we elevate the bed, the intracranial pressure gets lower. And when you put the rat in the normal position, it becomes normal. This is the same graphic, but with different scales, showing that it's the same graphic. Well, now I will talk about my work. It's in the middle of the work, but we have some interesting results with children. Our objective is to determine the comportament of the wave, the intracranial pressure wave in children with hydrocephalus, and try to see the relations of P2 and P1 that can show if the children is with hydrocephalus. And ultimately compare this system, this non-invasive system that we use in children, with our conventional methods to diagnose. US, TC, CT, and MRI. We studied children, patients less than 18 years here in the Hospital das Clínicas of Ribeirão Preto between 2004 and 2050. And we worked with children in ambulatorial system and internal children. We split these children in 3 groups. Group A, children with hydrocephalus, but that was clinical compensated without any surgery. Group B, patients with hydrocephalus that has to be operated, or with a shunt, ventriculoperitoneal shunt, or ventricular atrial shunt, or endoscopic ventriculostomy. And group C, patients with acute hydrocephalus or patients with elevated intracranial pressure. This is the more important patients. And our inclusion criteria was children below 18 years, patients with hydrocephalus in this Hospital das Clínicas, and patients whose fathers agrees, whose parents agrees with the experiment, or not experiment, with the study. We excluded patients that we couldn't see because they had to do some emergency surgery, or patients with infection or circulatory problems, shock. Well, we measured the intracranial pressure with non-invasive system for 5 minutes in the horizontal position with hardware provided by Professor Cérebro and Dr. Gustavo of the São Carlos, and we performed one measures before surgery and 1 day after surgery. And in the group B, we performed one measure during the normal segment of this patient. This picture is very interesting. I was with Dr. Sergio in this day. We were in the ICU. This is a children with lots of monitoring and access. In here, we could put the sensor. This is the aspect of the intracranial pressure we can see when we are monitoring the student to be sure that we are seeing the intracranial pressure. After this, we don't have access to the results immediately. We have to do some analysis. It's not with me. I'm a medical. I can't see. I don't know what's mathematical. But Professor Sergio and Dr. Gustavo are very good with this. Our preliminary results. We monitored 43 patients during this period. Unfortunately, 18 patients was excluded, mainly in the beginning because of the data was not good. We had lots of problems with hardware and software with the sensor. We could include 25 patients. 15 patients were processed. 1 patient is in the group 1, 12 patients in group 2, B, and only 2 patients, the more important patient, in the group C, the patient that has this compensated hydrocephalus. This is the data extracted from this. It's very interesting. Here you can see the P1, P2, and P3. And this is our results. The 15 patients with a median of 8.1, median of 9 years. So students, patients in group 1, group 2, and group 3. These two from group 3. But the most important thing here is this P2 and P1 relation. Here in group 1, in group 2, the relation is below 1. And here in the group 3, the relation is more than 1, showing that the P2 wave is higher than P1. These two patients, we could not see the intracranial wave morphology, probably because we are not monitoring intracranial pressure, but probably arterial pulsation, probably because the wave was not so good. Well, I will show here the patient number 14. It's a patient with 13 years with acute stenosis. He has headache, 3-4 months of headache. And we monitor these patients the day before the surgery. Here we can see the P2 higher than P1. So he performed a ventriculostomy, endoscopic ventriculostomy, and I monitored him the day after the surgery. Here you can see that the morphology is not the same. P2 is a little lower than P1. And the relation is below 1. This kind of patients, when we do this kind of surgery, the intracranial pressure doesn't get so low as when we do some kind of shunt. So we expected that the intracranial pressure of this patient gets lower, but in 3 or 4 weeks. Well, we presented these results in the Brazilian Congress of Pediatric Neurosurgery this month in Belém, and it was the second best work in this Congress, and we will present this work on this week in the SBPC Congress. Well, right now we have to include more patients on group C because we only have 2 patients, and we will try to do a group D with normal patients, normal children in Araraquara. Thank you very much for your attention. Any questions?
Muito obrigado. Thank you very much, Matheus, for
Thank
your
you.
talk. And I wonder if there's any question from the audience. Yes?
Regarding the band that you put on the head, is the signal in phase with the heart pulsation?
It's a problem, but the wave of heart pulsation is different from
No, the heartbeat.
But
Is in phase with the heartbeat?
If you put
Okay.
the intracranial pressure occurs when we have the heartbeat, but the wave is quite different. When we put in the
So-
artery, like here, it's very different. You can see.
I see. So the first one is the heartbeat, and then there's the...
You were talking about the morphology of intracranial wave?
Yeah.
Yeah, the first one, the P1, is the systolic beat.
Okay.
The second one is the reverberation of the systolic in the skull and then in the brain.
Okay, I got it.
And P3 is the closure of aortic valve.
Thank you.
It's not very easy to work with children of this age because they move, there's a lot of noise. So the work of Dr. Mateus is not an easy one. The most important thing is that the mother should be present.
Yes, always.
It's a very interesting psychological thing. When the mother is there, then it's possible to work with the child. So it's not very easy.
But Professor Sérgio is good with children too. They like him.
Yeah. Well, anyway, this is an objective to introduce this in pediatric surgery here in pathology, and we hope that we can continue. And I thank you very much for your help with
Thank
all
you.
this. Thank you, Mateus. Now, I'm going to give you a present. I'm the last speaker. I'm not going to talk anything. I'll just leave you for the coffee break because I think you have heard enough about ICP and other things. So all I would like to say to close this is to say that we have many objectives and dreams about what we are doing, and that's a component of the work of science. If you separate the dreams from the objectivity, then you lose the most important part, which is motivation. But I cannot close this without thanking again to all the people who helped us funding our research, especially the Foundation for Research of the State of São Paulo, Ministry of Health of Brazil, and most of all to our good friend, former director of the organization, Pan American Organization for Health, Dr. Felix Rigoli, who is here, and for whom I would like to ask an applause of thanks from all of you. Thank you. So we will have a coffee for everyone, and thank you very much for coming.